Very good morning, everyone. I am Jagdish. Welcome you all to the second day of National Training Workshop on Weather Radar. Today we have 4 sessions and we will discuss more on the application part of Weather Radar. So without further delay, I would like to invite Dr. Renzo Becchini for the talk on microphysics, DSD models, and precipitation process. Welcome, sir.
Sharing it. Good morning, everybody. So this talk is about microphysics. And can you hear me? Yes? Okay. So the idea is to start from the building blocks, which means drop size distribution. And this part describing the DSD, drop shape, like drops for velocity. These are basic things. Maybe I will go a bit fast at the beginning because probably most of you are already aware of all this stuff. And then describe more in detail, the impact of all this microphysics on the radar observation. So talk about the warm rain and cold rain process from the point of view of radar. So what the radar sees and how the radar observations are related to the microphysics of precipitation. And then, last part where I will talk a bit more about the morphological, phenomenological structure of precipitation system, both stratiform and convective, with specific features that we can see in the radar imagery and can help characterize the type of precipitation. So let's start with the DSD. So we know that in this image represented a few drops in the radar volume. Every drop has its own characteristic, is velocity, and there are only 8 drops, but we know that typically in a radar volume we can have millions of drops at the same time. So since we observe so many drops, it is very important to characterize how these drops are distributed, to get some information from the radar observation that makes a measurement of an ensemble of drops. So typically, the drop size distribution, these are a couple of DSD in rain, is represented by a 3-parameter equation where n of d is n0, which is the concentration parameter, p to the mu, which is a shape parameter, and this is the shape of the distribution, can be like this, or can be more like this, or can be exponential when mu is equal to 0. And then we have the slope parameter, lambda, that gives the slope of the DSD. So in the DSD, this DSD model is used for different particles, rain, snow, hail, and there are subtle variation. For example, in snow, many times the exponential distribution is used, so the shape parameter is removed, and this is enough to characterize. And here you can see, for example, how a distribution of snow particle evolved subject to aggregation. So from an initial distribution like this, the slope actually is modified by aggregation, which increase the number of large particles and decrease the number of smaller particles. And another example, in hail, also a power law distribution is being used. In this case, the slope parameter is removed, and the 2-parameter function can be used to represent the hail size distribution. So this is, you've seen this already. So this is illustrates the radar sampling geometry. So it's not, I don't think we need to go further into this, but just to remark the fact that the radar observes so many DSD, so many particles at the same time. And this is a sample of about 50 drop size distribution from a disdrometer. Disdrometer, we already talked about this. So I think that most of you are aware and have been using data from disdrometers. And this is a figure just to relate what the radar observes. The radar observes the drops within a volume. And I mean, the size distribution of drops is typically is represented as the number of drops per unit diameter per unit volume. So the number of drops in this cube, typically. But the disdrometer measures something else, measures a flux of drops across the surface. So when comparing radar and disdrometer observation, we need to take this into account and go from a flux of particles that is measured by disdrometer over a very limited surface to a volume. And to do that, we need the particle fall velocity that can be either derived from the particle size. That we can see there are relations to relate the velocity of the particle to its size, or is directly measured because some disdrometer measure the particle velocity in addition to the particle size. So having said that, these are a couple of examples of DSD size distribution. This is a distribution with a positive shape parameter, mu is equal to 2.4. So it makes this shape here with a lot of relatively small drops. And this is another distribution with negative mu, which is more infrequent. Typically, mu is 0 or positive. And if you have, and also there is a fit, the dashed line with a two-parameter distribution, the exponential distribution. And normally we represent on the logarithmic y-axis, and in that case, the intercept is just log 10 of n0, and the slope is lambda times a constant, log 10 of e. Okay, you've seen this already. So just to remark, this is probably very useful to understand the relation between reflectivity and rainfall, and to understand the limit of using the reflectivity. So it will be very useful to understand what comes later, what the dual polarization observation can add to reflectivity only observations. So in these cubes are represented on the left, a monodisperse distribution of drops all the same size. There are 5,000 drops in 1 cubic meter with the size of 1 millimeter. And here we have another monodisperse DSD, but with 2 millimeter drops. And here you see the expression for reflectivity and rainfall rate. So the most remarkable thing is that reflectivity depends on the 6th power of the diameter, while the water content depends on the 3rd power of the diameter, and the rainfall rate is slightly more. We see shortly 3.7 approximately. So there is a big difference. And depending on how the DSD, on how the particle size are distributed, there may be a wide variability in the relation between C and R.
So,
yes.
Yeah. So it's like that previous one. So you think concentration is more important, or because the relation, if you see mathematically, it is G to the power 6. 6 times it will be more bigger.
Mm-hmm.
So can you tell us like even if it is a 2 mm drop, so it's 6 times 2 means 2 to the power 6.
Yes.
So whether that is more important in reflectivity, the size and the concentration, which is more dominating in reflectivity?
Well, both are important, but the fact that the dependence on the high power means that even if you have a single drop with a large size, it will dominate completely the reflectivity. So actually, these are extreme examples, no, just for the scope of illustration. Here you have 5,000 1 millimeter. So you can calculate that very easily, even with the phone, that the reflectivity, if you consider the expression for the reflectivity factor, which is the integral of d to the 6.
It's like 5,000 only.
Yeah, log 10 of 5,000, yeah, 37, right? And then if you consider a single drop of 4 millimeter, 4 to the power of 6 is 4,096, which is
so
almost
similar.
5,000. I mean, I should have done 4.1 millimeter to be precise, but but then you see that they have the same reflectivity, which is 5,000 in linear units. Then you take the log and take you have 37. But you can see that the rain rate is completely different because it's a lower moment of the diameter. So between these two extremes, there are, I mean, the reality, which is the DSD. This is an exponential DSD, which is a typical DSD of rain. But you can see that the larger drops are very few, of course, because the slope is negative. And depending on actually the tail of the distribution, you can have large differences in the reflectivity compared to the rain rate. So for a given reflectivity, typically you may have 1 order of magnitude variability in the rain rate. Yet, I mean, with the two, considering these two extreme examples, we have 2 order of magnitude difference, but typically 1 order magnitude is possible. So you can have 35 dB reflectivity and maybe have a rain rate that can range between 3 and 15 millimeters per hour, depending on the actual shape of the DSD. So this is a video. I was actually okay. To see how the this is an old video, and it's much more unstable respect to Chandra's video yesterday. I'd like to steal that video to replace this one. So in this, but you can still appreciate how it drops. This is a laboratory experiment, but it's very close to what happens in reality. So you can see the drops oscillation and orientation varying a little bit, and there are a lot of studies on particle oscillation. There are axis symmetric oscillation, mainly that we have seen yesterday with a drop being deformed like this, and also transverse oscillation like this. And I think both can be appreciated in this video. So actually, this is very complex. I mean, the behavior of a single drop. But since the radar sees millions of drops at the same time, we need a mean drop shape model. So it's typically we can rely on a mean drop shape model to characterize the DSD. So, okay. So this is a drop shape of a Virgin triangle, which is one of the most used. There are other models. So the red line are actually the Virgin triangle complete three-dimensional model of the drops. And the dashed line is referred to this polynomial approximation by Brandes, I think, which is another useful approximation that is very frequently used. So you can see that the main difference is that the Virgin triangle model has a more flattened shape with respect to this approximation, but for most of the calculation, I mean, this simple approximation is typically enough. Well, this is summarizing several relations for the drop shape. So you have the raindrop diameter on the x-axis and the axis ratio on the y-axis. So one is spherical, and typically drops smaller than 0.51 millimeter are considered spherical, and above that you can see that the DOS becomes more oblate. And in reality, there is also, I mean, this process marks aircraft observation from this paper, And in reality, it has been seen that respect to the aerodynamic equilibrium models, drops tend to be a bit more spherical, especially in this size range, due to these oscillations that make the drops a bit more spherical than how it would in still air. Okay. So then the next important relation that we need is the terminal fall velocity. Again, this is a raindrop diameter, and this is a terminal fall velocity. So there are few relations. This is another valid approximation to a polynomial function, and this dotted line is this from Atlas and Goodrich 3.78 d to the power of 0.67. This is not as close an approximation, but it's very useful because we can replace b in the integral, and then we get a simple, very simple analytical form, and we get an idea of the moment of the exponent, which is needed in the rainfall rate estimation. So the water content, of course, would be d to the 3, and then the rain rate is d to the 3.7. So this number is it's very useful to remember and to compare with the moment of the radar observable. I mean, for the reflectivity is 6, and we will see shortly for KDP what this will be. So now, having characterized the drop shape, we know we have a model for the drop shape. We can model its orientation. So typically the drops are oriented vertical, but typically the orientation may vary with some spread with an average of 0. And characterizing the drop with these models, then we can do electromagnetic scattering simulations and calculate the radar parameter for individual drops of any size. Just a premise. So typically this gamma function, it's a 3-parameter distribution, is very useful to use a modified version of this, which I think many of you already know, which is a normalized drop size distribution, N of D, which is expressed as a function of NW and D0. So this form is useful, for example, to compare DSD from very different water content. And actually, you have the normalization of the diameter to D0 and the normalization of the particle concentration, which is expressed as a function of W, the water content, respect to D0 to the power of 4. And you see that when you have these DSDs in this form, and then you go to the normalized version with D over D0 on the x-axis and N divided by NW on the y-axis, all the DSD collapses to the same point, and then it's much easier, for example, to compare different DSD in very different rainfall rates. So now to the radar parameters. So making this scattering simulation for a wide range of DSD, I think this comes from several thousand observed DSD observed in very different precipitation regimes. Then you can plot, this is a 3D plot of the 3 radar parameters, C, CDR, and KDP. And then you can see and study how the radar parameters are related among each other and with other precipitation characteristics like water content or rainfall rate. And in this figure, then if we look at the 2-dimensional plot like KDP versus VH, CDR, CH, and KDP versus CDR, we can see some interesting things. So if we focus on this, which is the relation between CDR and reflectivity, I think you have seen this type of functional dependence. Typically, CDR increase with reflectivity. But of course, it's not a single line. There is a scatter, and these 2 lines, the dashed line and the dotted line, represent different values of NW. and NW increase in this direction. So it means that if we fix a reflectivity value, the CDR will be lower if NW is larger, and CDR will be larger when NW is lower. So what do you think would be if we let's assume that we have a rainfall of 30 dBc. We are observing 30 dBc in the rain, and CDR, you see, may vary between about 0.2 and 1, let's say. So what do you think will be the larger rain rate? The one with the lower CDR or the one with the larger CDR? From what we said until now, would you be able to guess which will be the... Yes, approximately, but yes, I'm wondering if you will get this is an approximate value, which may vary, but if you also add the information from CDR, if you have a low CDR associated with the 30 dBc, respect to a large CDR, what will be the CDR that gives you the larger rain rate? The lower CDR or the larger CDR observation? Let's say that you have 30 dBc, 0.2 CDR, or 30 dBc, 1 dB CDR. No.
Drop diameter.
Yes.
In that case, the rain rate will be more because rain rate is dependent on the drop diameter.
No, it's counterintuitive at the first, but it's exactly the opposite. Yes, because we fixed the reflectivity. So you're fixing the reflectivity. So if the reflectivity is fixed and the DDR is low, it means that that DSD is dominated by small particles. Okay? It's if you remember that the cube at the beginning is going back to that. While if we have the same reflectivity but very large CDR, it means that we have distribution with large drops and lower, smaller drops. So in that case, they give the same reflectivity, but the rain rate will be much more for the lower CDR. So this is, it takes a bit to assimilate this, because normally one see large CDR, oh, it's a large drop, so large rain. But
basically the DQ, the cubic volume,
yes,
in the water liquid water, that counts more number of drop, more liquid water content, then you will get more rain.
yes, exactly, yes. So then we have these other functional relations, and also in this case, you can see as KDP as a different relation in CDR. We will come. This is for S-band. S-band, yes. So it's almost Rayleigh stuttering. But I mean, it will be very similar for C-band or X-band qualitatively. Of course, there will be differences. For example, CDR, you will see higher values here for C-band, of course. But for qualitative reasoning that we are doing now is the qualitative behavior is the same.
3 gigahertz. Yeah.
3 gigahertz. Yes. Yes, but
for 5 gigahertz also it will be same.
Similar, qualitatively similar, but not the same. CDR will be higher if you have C-band. I will show you later. I have some other plots also for C-band and X-band. Yes.
So that median, that is a median line, and then 95 percentile, that dotted line, right?
Well, the dotted line is just different values of NW, so probably we are about the 90%. I don't remember exactly. So it's the two extreme of the distribution. I mean, the average was 3.5 NW.
Okay.
And yes, the other two lines 2.5 and 4.5. Yes, you can see visually that maybe 10, 90% quantile. Yeah.
So this is like for any specific rain event, like convective or stratiform, you just consider whatever the raindrops available.
Yes, actually, I mean, this is having the dual polarization observations, then you can actually derive directly or indirectly information about the DSD and then apply a better relation to estimate rainfall.
Okay. And this axis ratio, So you have used the Brand and Chang,
Bird and Flank, yeah.
Bear and Chang.
Yes. That will also cause some variability, of course, depending on the model or the assumption that you made about the drop shape, which can change a bit. But of course, I mean, there are, you know.
Yeah, so the items, why there is a series of question I asked, like suppose if we can consider like, because ZDR is very noisy, it doesn't look as it is looking here in this figure.
Yes.
So in the real time, you will see some abnormal ZDR in like
Yes. Yes.
Radar. So whether can we use this as like a benchmark, like whether we have to follow the standard of the distribution?
Well, this is mainly for illustration to understand what value the dual polarization can lead. So of course, for S-band, you can use CDR. Of course, it has some noise. And look at then after me, I have a presentation specific on rainfall estimation. Then it's a matter to match, I mean, the error measurements with the information, with the added information that CDR can bring. So CDR can bring added information by actually helping determine the two parameters of the DSD or directly into a two-parameter formula to improve the rainfall estimation. But of course, if the uncertainty on the measured CDR is too high, then you have a two-parameter relation instead of one parameter relation, then you have propagation of errors and you can even get worse results. So one thing that people do, for example, you can do spatial averaging of CDR. So instead of considering a single range gate, you average over a few range gates in range or even in azimuth.
Like consider like 1 kilometer or like.
Yes, for example, to reduce the variability of the observation and go below the typical limit would be CDR at least 0.2 standard deviation, less than 0.2 to be used in quantitative application. I mean, if it's close to 0.1, even better. So, for example, you can consider spatial averaging and then reduce the spatial resolution of the estimate, but using the dual polarization information. So this is, of course, the application is really dependent on the goodness of the radar and a lot of other stuff. And of course, for X-band, we also need to consider attenuation. Then it's there are other challenges.
Yeah. In the relationship between the horizontal reflectivity and the specific differential phase, what I see that after 35 dBz, there is a sharp increase. So can you explain in terms of the liquid rain, how does this variation takes place?
Okay. Yes, KDP, as we will see also later, is related. Well, CDR is related to the mean shape of the particles, so it is not related with concentration. So you may have a single drop for you. I mean, 2 millimeter drop or 1 million 2 millimeter drop, and you have the same CDR. KDP, on the other hand, is related both to the concentration and the oblateness and the shape. So for this reason, actually you see KDP increasing much later because DSD have many particles with small diameters that have.
So you meant to say that the concentration increases, that is the presence of more liquid raindrops.
Yes.
In the real atmosphere.
Yes, yes. So actually KDP is useful for rainfall estimation because it's related both to the concentration and to the shape. But of course, given that since the DSD normally have more small droplets, so you can see this increase only later respect to CDR. Okay, so this is what I was telling before. So CDR is related to the mean drop shape, and I mean, since we know there is a relation between the mean drop shape and the diameter, then it can be related directly to the D0, which is the median volume diameter, which is that diameter for which half of the volume is given by smaller particles and half of the volume is given by larger particles. So in considering Rayleigh approximation, we would get this line here, this theoretical line, which would mark the unique relation between CDR and D0. Now, with scattering simulation at different frequency, we get these results, and the gray shading is just a contour plot of the distribution of many simulations. So you see that at S band we have a relatively close agreement with the theoretical DSD in Rayleigh, and you can see that D0 can be actually estimated from CDR. So CDR gives you information about the median drop diameter or the mass weighted diameter, that is another parameter that is used to characterize DSD. One interesting thing that you see is that if you go to C band, you see quite a different when starting at around 2 millimeter diameter. You can see that this relation bends toward the larger CDR. So this is due to scattering effects. And you see on the other hand that X band is actually closer to S band. So this is interesting and actually makes X band for several reasons closer to S band than C band. And for KU band is also very similar to X band. So this can be explained with this. So this is a bit complex, but this is a three-dimensional representation of this backscattering ratio between horizontal and vertical. And you have the diameter here, and you have the frequency increasing in this way. So you see for a very low frequency, let's say 2-3 gigahertz, this is almost increasing steadily. And this is represented here by this dashed line. This is the Rayleigh scattering approximation. But then you see this peak that is moving in this way. So it is very large at low frequencies, but actually this peak happens at diameter which is larger than 10 millimeters. So it does not affect S band. But as you move to higher frequency, you encounter this peak at lower. It's lower in amplitude, the peak, but it's happening at the lower diameter size. So it means that the C band, this is C band, you have this peak around 6 millimeters. So it is still quite high, the peak, and it happens in a range of diameter that we can actually observe. While X band, we move forward in this direction, so the peak is much lower, and it happens at a smaller size. So now the effect is that if you consider a drop size distribution with many particles, you have a lot of typically raindrops up to 3-4 millimeters. So this peak is very often smoothed out. While at C band, if we have a DSD that contains even few large drops larger than 4-5 millimeters, then this peak can have a very consistent effect on the radar parameters, in particular CDR. So this explains why for the same D0 at C band, we are getting much higher value respect to S band and also to X band. I don't know if this is clear.
Yeah, so I was supposed to ask this question. It's because like C band observe some ZDR, okay, but the same ZDR maybe we use to like in
X band also, but the value of the drop size will be different.
Yes.
So then when we compare it with the like ground-based meter and we do some kind of fitting to match so that we can say our result is good.
Yes.
In that scenario, what will be your suggestion? So how to look at those?
Yes, when you compare with DSD, as we will see in the presentation that we have this afternoon, you have to calculate the radar parameter using appropriate scattering assumption depending on the band. So we will have a simulation calculating the CDR for X band and for C band from this meter, and we will get very different values in some cases. Then to compare with the radar, you have to make sure that you are calculating the radar parameter from the distrometer with a scattering simulation, not a Rayleigh scattering. Because for C band, indeed we can actually observe 7 dB in rain, while for expand, typically we do not observe more than 4. And this is, a practical observation. So if you simply calculate CCR using radius scattering and compare with the C or expand, then you may get, stronger results.
So this figure shows like S band and X band ZDR is good.
Yes, in principle, this is of course without considering attenuation. But this is another topic that it comes later. But intrinsically, from the scattering behavior of the targets, the behavior is much similar between S band and X band than C band. C band is a bit just because this peak happens to be at a moderate amplitude in a range that is frequently observed. So it has a larger impact on the radar parameters respect to X band, where we observe for smaller diameter, but you can see the amplitude is very small. Yes. Yes.
Can you hear me?
Yes.
So, thanks, because yesterday, it was late in the day, I cleverly skipped this figure. And, C-band, many times in Europe, because a lot of people have observed 5-6 dB of CDR. So everybody was scratching their head. Why is this happening? But more importantly, practically speaking, it looks like it's a slam dunk with the X-band. But when you practically use the ZDR from X-band, you have to correct for attenuation before you start comparing with the astrometer. So that's put some extra uncertainty in the process. So you have to keep that in the back of your mind.
No, means what happened, we observe that value, like yesterday I told, like sometimes 4 dB like ZDR, but we don't know that is actually correct.
No, it's our first what I'm saying is, before you do that, even interpret it, you have to correct it for attenuation.
Yeah, sure.
After that, if it's 4 dB, it is 4 dB.
I think it's correct. I will show you an example from our radar. We have up to 7 dB CDR. It's reliable. It can be based on this.
Yeah, so like as I mentioned, Professor, like in Mumbai, sometimes you observe 3 and 4 dB. Sometimes all of a sudden it is showing like 2, 3, and then suddenly a big patch of like 3-4 dB, and again it looks good. So we don't know that whether that is due to that.
Was it summer convection?
Yeah, post monsoon during like October time, September and October time we observe. Yeah.
So during convection, then 90% of the time, this is my opinion, ice has not fully melted. So that makes a giant drop, and that creates the extra high CDR.
Yeah. So.
Yes, typically these large values are due to melted ice particles that are very oblate, more oblate than typical raindrops. And this actually, I come back later, makes it also a little bit challenging to use. On X-band, they developed hail, the first rain hail discrimination based on ZDR. You may be aware, because typically ZDR is increasing with the Z in rain, but in hail, they say typically hail is spherical, so it should have 0 dB CDR. So when you have high reflectivity and very low CDR, close to 0, you have hail. In practice, at C-band, we almost never observe this, because there is maybe always be some partially melted hail that will give a strong CDR return. So it's quite different. Yes.
Apart from the attenuation and the expand frequency, apart from the attenuation, what are the other ways that can influence the ZDR measurements?
Well, I would say mostly, artifacts like ground clutter. In our region, we have a lot of RFI, radio frequency interference. It's a ZDR. The problem of ZDR. ZDR is the difference between two very similar quantities. So it's a very small. It's very difficult to measure with a high accuracy. So it's sensitive to any artifacts. So in our case, I would say clutter and radio frequency interference are two big challenges for us to get a clean CDR. So actually, yes, this is what I was mentioning before, that the CDR we use since the 70s to, for example, to partition. It is the CDR DH space, and IDIN in the 80s, there are this function to separate rain from hail. So they say that if CDR is on the lower left, above this line, is rain. If it is below, it is hail. So this is useful for S-band. It has been applied and has been very successfully. It is less, straightforward for C-band due to this Rayleigh scattering. So I will come back later on this, but this actually tries to summarize the information CDR may bring. So typically we have we may have very large CDR columns. I have example later. So in the developing stage of convection, and you may also have a large CDR in melting snow. So in the bright band or just below the bright band. So now let's change variable. Let's talk about ρHV, the correlation coefficient, which is yes, actually a very useful parameter for many applications. It can be especially useful, for example, to discriminate between meteorological targets and non-meteorological targets like clutter or interferences. And it can be very useful to separate the rainfall region from the snow region and the melting layer. And because ρHV is brings information about the collective behavior of the ensemble of scatterers. So it's a correlation between the signal in the horizontal and the signal in the vertical, which means if for example, in this idealized case, if you have only spherical drops, the correlation is exactly 1, because the horizontal signal will be perfectly correlated with the vertical signal. If the drops follow the axis ratio model that we have seen before, you will still get a very high correlation because there is a correlation between the horizontal and the vertical. But if you have different shapes and orientation in the same volume, then ρHV will drop to a much lower value. To give you an idea, in rain, you typically have ρHV above 0.98. So it's very high. So when ρHV drops below 0.97, 0.95, typically means that there is a mixture of particles. So we are not observing pure rain, but probably there may be some hail or from snow, melting snow, something like this. This is of course quite extreme. Less than 0.9. Normally you can only observe within the melting layer when you have a high degree of mixing of different shapes and orientation. And then FDP is the differential phase shift. So in this plot, we try to represent this. You have the wave in the horizontal and the wave in the vertical. And due to the fact that the signal propagates through a medium which appears as more filled with water in the horizontal respect to the vertical, you may have a lag in the phase because the propagation velocity will change. So if you have only air, of course, the phase will be the same. If you have spherical droplets, the phase, of course, will still be the same. There will be no change between the H and B. But then if you have oblate particles like raindrops, then there will be a lag between the phase in the vertical respect to the phase in the horizontal. And this is what we call FDP, the differential phase shift. So there will be an increase in the rainfall region where particles are sufficiently oblate. So if you have drizzle, your FDP will be close to 0, will not increase. But if you have oblate particle, it will increase. And then what we are mainly interested in is the range derivative of FDP, which is KDP, the specific differential phase shift, which will show, in this case, idealized, of course, which will show a constant value. So we go from a cumulative, the TDP is constantly increasing. It's a propagation measurement, and this is what the radar measure. But then taking this derivative, we get a local information that we can relate to the precipitation. So this is an example. This is a TDP filtered. Of course, the observation TDP is more noisy. And then this is KDP, which is the range derivative of TDP, sorry. So this is a formula for TDP, which is related to the forward propagation. And this is expressed as the real part of this polarization term. I will not go into details, but for rain, it can be shown that this polarization term is proportional to 1 minus R, where R is the axis ratio, A over B for the rainfall. So this means that if this is of the order of T, because the axis ratio in turn is almost linearly related with the particle size. So we have D to the 3, it is proportional to D. We have for rain that TDP is proportional approximately to D to the 4. So if you remember, rain is proportional to D to the 3.7. So this is very close. This is why TDP is so useful for rainfall estimation, especially in heavy rain, because it's drop size dependency is much closer to the dependency that we have for rain with respect to reflectivity, which has D to the 6. On the other hand, for crystallized crystal, TDP is typically proportional to the third power of D. So it's also in this case, it's very useful for ice water content, for example, estimation. So now I would go to the second part of the presentation, which is we've been talking about observation at instantaneous observation, local observations, and I want to talk about how the dual polarization parameter varies due to different processes. So we look at variation mainly in the vertical upon different precipitation process. We can have collision coalition, for example, for which both C and CDR increase. You can have breakup, leads to a decrease of this parameter, and many other parameters, many other processes, both in the warm rain and in the cold rain. So maybe if you want to make a small break and have some, if you have any question on the previous part, we can, and then we, okay.
Explain the rho HV with the different shapes. So I would like to know that if it is a non-meteorological, how much will be the rho HV?
The rho HV can be as low as 0.5 for non-meteorological, but it varies a lot. So normally, for example, it is used in cluster identification, in particle identification, and normally below 0.8, it can be, it's a good indication of cluster. Sometimes it's difficult to discriminate between the melting layer, because sometimes also the melting layer, especially close to the radar, when you have your beam is small, so it gets only, the melting layer is not smoothed with rain below, can be very low, even 0.7. But then there are other parameters that help discriminate between melting layer and cluster.
One more question for that.
Yeah.
Radio interference, when you face the radio interference with the airplanes or anything, you want to discard that data, and you have any way to correct it?
No, it's a good question.
I'm sorry.
Exactly. But you say radio interference from airplanes? No.
No, but when we see the radar observations, it will be either radio interference, and we observe that at the same time some airplanes are going, saying the spectrum is, the data is corrupted. So under that conditions, you just told that ZDR is very sensitive, because if the ZH minus ZD, it's a very small value there. So it is very crucial for this other correction. I just want to know the radio interference or any other interferences, how it can be.
Okay. Yes, actually that should be done at the level of signal processing. At the signal processing level, it's possible to identify on the IQ time series, you can actually go and try to remove actually the IQ that comes from the interference and the
IQ.
yes, on the IQ, yes.
If I have only moments,
If you have only moments,
no way.
Yeah, only moments tough luck.
yes, you have to reject.
That's right.
And, yes,
You have to discard that data.
yeah, this is actually what we do now. But yes, there are you know there are research going on you know this IQ data processing for RFI removal, identification and removal. And it is going to be, I mean, in Europe, it's a really huge problem. I don't know here, but the C-band in Europe is overcrowded. And typically where you have the radar, it's particularly tough because you have radar in good visibility.
If
and
you have
have,
IQ, then you can process it with that.
sorry?
If you have IQ data, then you can do the.
Yes, if you have IQ data, but normally you don't, I mean, it's difficult to save all the IQ data and
Renzo,
yes.
Regarding this 5 dp and KDP, if we have 1 cubic meter volume, and so let's say there are 100 drizzle and rain drops, and if we remove say 20% of the rain drops and put hail particles, so what will happen to the 3dp and KDP measurements?
So actually, if the hail is spherical, as it's normally assumed because it's either tumbling or, yes, KDP will be reduced. So, and KDPs will only be sensitive to the rain portion of the, of the population of particles in the volume.
So you cannot discriminate the rain with hail?
Not alone, no. Not alone. I have an example right at the end, which will show an example with yes, only hail and rain with hail, and how you can discriminate, but you cannot do it with the KDP alone. You also need CDR. With KDP and CDR, then you can say if it is a mixture or if it is hail alone.
Thank you.
There's a question from the back from
Say previous slide.
that question from the back for a long time. So get up, I can see you, nobody else is seeing you. There was a question from the back for a long time. I say so your hand many times.
Yes, sir. So in this, like, how can we physically understand KDP? Because
okay. How can we physically understand KDP? So
Did you understand the question?
I tried. So actually, let's start with what we observe is PDP. PDP is the phase difference between horizontal and vertical. So you can imagine your wave traveling and propagating through precipitation. When it encounters rain, it will slow down the speed of the wave. So the phase will be like compressed. And the same for the vertical polarization, but the vertical polarization sees less rain because it is vertical. So the phase change will be less. So this will cause a phase difference between the horizontal and the vertical. So this KDP, as you see, is continuously increasing, it's monotonically increasing in rain. Okay. I mean, if you don't consider noise in real observation. And it gives you, of course, it increases more when there is more rain. So its local derivative then gives you an information of the amount of rain at a specific location, because the derivative is local. So you see when the slope is higher, like here, then you have a peak in KDP. When the slope is lower, close to zero, then KDP goes down. I don't know if this is a critical explanation.
The relationship between KDP and 3.67, 3.67 at the moment.
Okay. So this is actually the definition, and I mean we can discuss later the details, but basically from the is the integral of the real part of this polarization term, which is related to the forward scattering, not the backward scattering. And this parameter for rain can be shown to be proportional to 1 minus R, where R is the axis ratio of the drop. And the axis ratio of the drop is roughly proportional to the diameter, because increasing the diameter, you decrease. So this is proportional to D, to minus D, of course. And then if you multiply D, D to the 3, you have D to the 4. So very roughly, we can say that TDP is proportional to D to the 4 in rain, while rain is proportional to D to the 3.7. So they are very close. It means that TDP is much less sensitive to the DSD variability with respect to reflectivity. Because reflectivity, if you have a large drops, it will impact a lot of reflectivity, but not as much the rainfall rate. KDP, yeah, more or less the same functional dependence. So there is a better relation between rain and KDP.
Yeah. Hello.
Yes.
Yeah. Ranjan, nice talk. So actually, I'm from the modeling side. So I'm very much use this radar for the process studies basically. So my question is, see, we are talking about the size distribution of rain and other cloud hydrometers. And we have seen that some are gamma distributions, and some are power law, and some are master problem or something like that. So here, like power distributions. So my question is that can we make a generalized such distribution for all hydrometers?
Yeah, actually, I mean, the most used form is the gamma size distribution. This is the most used, which is the 3-parameter gamma. So I just showed at the beginning some example, because in some contexts, simplified 2 parameters are used, either the exponential or a power law. But in general, the gamma distribution can be widely used and represent any type of particles.
Yeah. Secondly, we are using sometimes the modified gamma distributions. So point is that mu, whether it is varying from one region to another regions.
Regions.
Yeah. So is there regional variability of the mu in gamma distributions?
Well, there is a variability of mu from you can have mu from negative to positive. Typically, I think that from statistics, probably the most likely is around 2 or 3. So there is this type of function. But yes, I would not say.
Sometimes we use that intercept and slope from the distributor. So what is your suggestion? Can we get better from the radar to fix this slope and intercept?
You can actually use radar observation to calculate the slope and the intercept. So if you assume, for example, a 2-parameter, to simplify, you have CDR, then you can calculate the slope from CDR, and then the N0, the intercept from reflectivity, once you know the slope. But that is possible. Okay.
So third question is the fall velocity. So we are looking for the fall velocity parameters, and this is very important for the extreme rain.
So which parameter?
Fall velocity. Fall velocity.
Okay.
So the fall velocity parameterization can we do from this radar estimation?
Well, if you point vertically, of course your measurement is mainly the fall velocity, unless you have a very strong updraft. Of course, what you observe with the radar is the particle velocity, which is the sum of the air velocity and the fall velocity. So when I also have a picture later about vertical pointing, Doppler spectrum, and you can clearly see the particle fall velocity, because normally it is dominant. Otherwise, on low elevation scanning, that is more difficult. There are algorithm processing to derive the 3-dimensional wind from lower scanning radar, like BBP techniques. So you actually consider all the observation at several elevations, and then with some assumption about the uniformity of the wind field, you may be able to derive also the vertical components, but that is not direct observation.
Thank you. And the last question, actually, Professor Chandra was mentioning that small jitter that was basically from Mumbai. It is from the snow or ice process. So do we feel that in the Mumbai there is a possibility of the snow and ice formations during winter? So I am not sure. Yeah, post monsoon. So unless until there is thunderstorm and okay, so there is a possibility of
Yeah. You mean there is a possibility to observe snow well, in general, I'm not expert in tropical meteorology, but I mean, I know there are some cases that you only have warm rain processes, but in many instances, you will have mixed cloud, even if much higher than we are used to at our mid-latitude, you will have ice particles above 5 or 6 kilometers.
My question is that during Mumbai, basically the giant CCN can play and make the bigger droplets. So my point is that whether it is coming from the rain formation due to the sea salt which is coming from the Arabian Sea, or it is due to the rhyming process. These two things can have make the bigger droplets. So this is my question, Professor Chandra.
So, myself and friends who are involved in similar projects like this, but though not the monsoon season. Warm rain is always of interest because it's very shallow. And then we do expect warm rain. But then when it comes onshore, then the thing is, we can postulate, but because we have low polarization radar, we should have radar observations. And then sometimes when this rain hits the slopes, then you can actually, we have, I don't think we have those data right from the rainfall actually goes up, not for this presentation. No,
Yes,
not-
the Olympics, you mean the orographic enhancement? Yes, yes, I have.
You have here?
Yes.
No, not right now. But
Okay.
later when we talk, you can actually see just by collision coefficients, rainfall rate going up. But the thing is, with all that I was trying to say was in summer convection, when you have radar, and then the storm goes very high, you definitely have ice, whether you are in Mumbai or Kashmir. Because a lot of times when you are in Mumbai, we are not used to thinking we have ice. That's what I was trying to say. I was not trying to discount the whole bomb rain process. It's a whole other ballgame. And so the thing about bomb rain is it's very shallow, so it has to be observed fairly well. And so we deal with that challenge all the time. If you want, you can show it right now. Unless it's disruptive. But I don't want to disrupt you.
No, it's fine.
Vince? Exactly.
Yeah.
Yeah, so regarding that fall velocity, so you can derive the D0 from the radar, and from the radar you can derive that fall velocity. You have shown the fourth order polynomial equation. Yeah,
Yes.
you have shown one fourth order polynomial equation, right? So
Yes.
so that can be used to derive the fall velocity.
Yes.
Even though you have the D0,
Yes. From
indirect
zero.
measurement will be there.
Yes.
So you can derive that fall velocity from there. And someone has asked whether you can derive this concentration yesterday, you remember?
Concentration, yes. Actually, you can derive from reflectivity. Once you have derived the slope parameter from CDR,
Yeah.
then you can use that. And
What's that? Yesterday someone has asked.
yeah.
Yeah.
So actually, yes. This is a case for this was during the Olympus campaign in California. This is a S-band. And you can see the melting layer. You can see actually below the melting layer, there is an increased reflectivity near the ground. And if we look at observation from a collocated KU band, which is actually even more detailed, this is a KU band scan up to 10 kilometers. You can see the melting layer here. And you can see that you have, after the snow completely melts, you have values around 25, 27 dBz. And then this is increasing towards the ground by actually about plus 60 dB. And at the same time, you have CDR increasing by about 0.6 cp. And this is actually a clear indication of collision coalescence in the warm rain. And actually, this gives actually the prompt to go further with the rain processes. Just okay. This is actually just what I wanted to introduce now. So talk about these rain processes starting from warm rain. So the first is actually collision coalescence and breakup, which are two of the most important processes in warm rain for rain formulation. There was a video here, but never mind. It's just showing, the drop shape and breakup. And so collision coalescence and breakup are mass conservative processes. So they just rearrange the drop size distribution, but don't change the overall water content. So in one case, the DSD is skewed towards larger oblate drops because collision, of course, will reduce. Okay. This is collision coalescence. Of course, the small drops are being collected by the larger drops. So the DSD, the slope will be reduced. I mean, the large drops will increase and the smaller drops will decrease. While on the other hand, drop breakup, which is happening soon, will act the other way. And of course, reducing the large drops and increasing the small droplets. So this is a simple simulation. So assuming a conservation of the rain flux from a given level, started from 3 kilometer height with a prescribed DSD. We assume a conservation of the flux, and then we simulate what happens as this DSD evolve falling towards the ground. So we can see this is the diameter and this is liquid water content. That's starting from this DSD, which is kept as the dotted line in the lower levels. Then we can see an increase in the tail of the distribution. The larger drops increase, while these smaller drops will decrease. And this has the effect of increasing CH towards the ground and CDR toward the ground, just like the example that we have just seen in the California example. And this is due to the fact that particles have different velocities. Of course, if different size and different velocities, because if all the particles were the same size and same velocity in still air, of course, they would never collide, and that would not be possible. But the fact that larger drops are falling faster, they will collect some smaller drops falling slower. And so this is
You want details?
Thank you.
So this is actually this example of collision coalescence in the warm rain. And yes, actually, this is an example. I don't know if we have time to also talk about ice processes, but this is a nice example of ice processes going on above the melting layer with a large PDP region marking probably rhyming and aggregation, and then dries growth, and melting and below melting further increase by collision coalescence. So typically we have a mix of warm rain and cold rain processes going on at the same. For us, it's quite normal at mid latitudes, but I think also here it is not uncommon. Then the other process that we can observe, and we have a clear signature from radar, is evaporation. Evaporation, this is the equation. This is an environmental factor. SW is the saturation water vapor. And you can see that the derivative, the change in the R is the radius of the particle. The change in the radius is inverse proportional to the radius itself, which means that the lower particle evaporates faster. So the impact of the evaporation increases as the process progresses because the particle size is reduced, and then the evaporation becomes even stronger. This is an example with a few drops, different sizes, starting from 3 kilometer height, and for two different levels of relative humidity. And we can see that even with the relative humidity quite high of 85%, the drops of 0.5 millimeter will evaporate completely after about 500 meters, while if, no, sorry, it's this one, after 1.5 kilometer. While if the evaporation is relative humidity is 50%, it will take only 500 meters to evaporate completely. And you can see how these smaller drops evaporate much faster. If you go to drops larger than 2 or 3 millimeter, then the impact of evaporation is relatively small compared to the particle size. And we can simulate the impact on the radar parameters in this case. So I should have asked you what you would expect for reflectivity and differential reflectivity. I mean, what would be the impact due to evaporation alone? If you have a DSD that is just subject to evaporation, so which will diminish mainly the size of the smaller particle, what would be the reflectivity, the impact on reflectivity? Increase, decrease, remain the same? Yes. It won't affect much in general, but if it affects, it will be which sign, which it will reduce because the mass is reduced. I mean, all the drops are reduced, the smaller are more reduced, so it will be reduced. Depending, the impact will actually depend on the shape of the DSD, because if the DSD has a larger contribution from small drops, the impact will be larger respect if the DSD has more contribution from larger drops. And for CDR, this is a bit more difficult to predict. Actually, this is the impact on reflectivity. For an exponential distribution, we have a decrease, but not that much. While for a distribution with a large mu, which means dominated by small drops and with a very small tail, then the impact can be very large also on the reflectivity. On the other hand, on the differential reflectivity, in general, there is a small variation or actually an increase in CDR, because CDR is, as I said before, is proportional to the mean drop shape, not the concentration. So if we remove the smaller particles, CDR will increase because it's sensitive to the average particle size, which will increase. But this also depends on the specific shape of the DSD. But qualitative, this is the impact. This is an example of evaporation. This is an RHI. You can see the reflectivity with those streaks, and you can see there is, if you only look below the melting layer, you see reflectivity even above 30 dBc, but then on the ground, there is nothing. So this precipitation completely evaporates before reaching the ground. And if you look at CDR you see is very small, 0.2, 0.3 dB. So this actually gives the indication that the DSD, in this case, just below the melting layer, was already dominated by small drops. So that means that it was prone to be subject to consistent evaporation. So actually, this can have also practical application. So imagine that your radar visibility is limited, and you can see only above 2 kilometers in this region. You see this high reflectivity, but you see very small CDR, and you know that there is dry air below. You can guess that this precipitation will not reach the ground. Instead, if you would have had like 1 or 1.5 dB CDR in this case, you would have guessed that the impact of evaporation would have been smaller in this case. Okay, the other process I'd like to talk is sedimentation. So what we talked until now can be represented as stationary processes. Both collision, coalescence, and evaporation can be represented as stationary processes, fixing, the flux or yes, the flux of rain or the flux of number of particles, and then you get a stationary profile. On the other hand, sedimentation is typically, and side sorting are typically transient processes that you observe over a very small period of time and then will disappear. So this is an example of initiation of precipitation from from a cloud, typically in the summer. So you see that when drops start to fall, the larger drops are falling faster, so are the first to reach, in this case, the radar volume. So there will be the first period where the radar volume will be filled with only larger drops, because smaller drops are falling slower, so will have not reached yet. So this okay. Okay, so this is just vertical velocity. Okay, and this can be represented in this case in the larger cube. Represented what could be the situation that you experience in the summer with a shower at the beginning. You only feel very few large drops that you can actually also run through the drops without being wetted by the precipitation. This is the onset of precipitation, because the larger drops are the ones falling faster and are the first to reach the ground. And you have this situation. For this, I calculated the radar parameters. So you would have a reflectivity of 30 dBc, a CDR of 3.6 dB, and KDP basically 0. Then, let's say after 10 minutes, when you have reached a stationary situation, that you have a typical exponential DSD typical of mature rain, you may have reflectivity much larger, 50 dBc, and only 2.1 dB CDR and KDP of 1.7 degree per kilometer in this case. So you see that in this case, radar parameters can help also characterize the stage of precipitation. This is very frequent to observe large CDR in relatively low reflectivity at the beginning of convection due to this transient process. So this is for sedimentation, I mean the fall. And yes, I can skip this, just to give an analysis of the reflectivity and differential reflectivity after given times at various heights. But this is what we have discussed. And size sorting is actually the same thing, but typically happening in 3 dimensions. Sedimentation is just the differential velocity, and size sorting is when we have a wind shear, even in the horizontal, not only in the vertical. This can lead to very specific features and CDR in the space. We have reflectivity here. We have a Doppler. This was a tornado case in the US. This was the location of the tornado. And then we have CDR. And you can see this region of very large value of CDR. This is called the CDR arc, they call it. And this is due actually to size sorting. So this is a vertical cut through this section, through this dashed line.
And so, go back to the previous slide.
Yeah.
So there are the areas where reflectivity is very low, like it's like moderate, like 30.
Yeah, yes.
But you are getting very high value of ZDR, like
Yes.
ZDR. Yeah. So how to understand this phenomena?
Yeah, I get that. Yes, it's come.
Actually, I thought you were interrupting me because it's not.
Yes, I also want that.
This will take a long time.
Okay, so then
we can. You want to continue now or
you can break.
break now? Because this will take story.
But the next is but I think we can finish.
Okay.
I don't know. We can finish 5 minutes and then. So this is vertical cut, you see reflectivity, you see the typical overhanging precipitation with the updraft here. This is differential reflectivity. You can see a very clear CDR column and also this region of very large reflectivity, which is the same that we were seeing in this PPI. So the explanation in this case, considering the Doppler velocity, we can see that there was a relevant shear in this layer here. So we go from 2 meters per second to 17 meters per second near the ground. So this shear here actually makes a larger concentration, large drops in this area, while the smaller drops, which fall slower, so they are exposed for a longer time to this shear, are vector toward the core of the storm. So this is an indication of size sorting. So there is a wind shear, and it makes a larger concentration of large drops in this case respect to here. Then these drops are also subject to the updraft. These isolines mark the Doppler velocity. So there is after actually they mark the convergence, the divergence. So negative divergence, convergence. So there is an updraft here. So these drops are carried aloft above the 0 degree level and make the CDR column. The CDR column is due to the liquid drops being affected above the freezing level. So where you normally have snow, which has a near zero reflectivity, you will have super cool liquid drops, which are oblate and make this positive signal. In addition to that, this size sorting will make that the smaller drops advected will be advected much further higher and will freeze. And the larger drops will, of course, will be subject to smaller advection because the fall velocity is higher, so contrast the updraft velocity, and will remain suspended. And very often you will see this signal aloft, which is associated to the first phase of convection. Not only in supercells, also in normal convection, we can see that very often. Not that all. This is on 4 kilometer height above the freezing level. But typically, CDR column extending up to a couple of kilometers is very frequent.
I have a question.
Yes. What is the base? The base typically we consider the freezing level. You know, for there are algorithms to identify. Normally, you consider the environmental freezing level, and you try to calculate the three-dimensional volume of positive reflectivity above.
And what makes that the negative CDR cap at the top of the CDR column?
So in this case, probably it's freezing and graupel. You know, at some point, the super cool drops will freeze, and actually this may be graupel or hail. I should look at corresponding reflectivity. Yes, actually the reflectivity is very high. Could be hail.
That's a regular characteristics of the CDR column, or for that specific to this?
No, this is a specific case with a very strong, this was a supercell with a large hail production. So in this case, we have this cap with negative CDR, which is likely due to hail. But we can have a CDR column in relatively shallow convection in the spring without hail.
Essentially, these are the proxies for the updrafts.
Yes, and you know the larger the extension in altitude of the CDR column, the more likely actually you have to have severe convection with hail production, because it is a measure of how intense is the updraft. Then the stronger updraft.
So as the updraft diminishes, the CDR column falls.
Yes, normally this is a transient signature. It will last maybe 10-15 minutes in the first phases. Then when the cumulus stage development reaches macro stage, it will. We have another example that maybe we can show later, and these normally precede the stronger reflectivity.
Yes.
Then there is a delay, a lag of about maybe 20 minutes. So you can see first the CDR column is still moderate reflectivity.
Is that basically the early observational indicator?
Yes,
for the
it can provide, yes, in advance a proxy for, yes, stronger development. Thank you.
We have another question.
So, how do you know it's the wind shear that causes size sorting, but not the strong relative wind, especially in case of supercells?
How do you know it's the wind instead of some?
How do you know it's the wind shear that is causing the size sorting instead of the strong relative wind itself, especially when it's the supercell?
Well, it's of course this is an interpretation. This is an interpretation based on the on the dynamics. So matching the dynamics information from the Doppler and the signature, the radar signatures. So what would be? I don't understand what would be an alternative explanation. Storm relative wind. No, actually, this is actually the Doppler. So this is not. This is the particle speed. Yes.
So there is a paper called by the name "Does Wind Shear Cause Size Sorting?" And they argue that it's necessarily not the wind shear, especially in case of supercells, but it is the storm induced wind, strong relative wind,
Okay.
caused by the storm itself, not by the background.
Okay.
Yeah.
Yes. It could be. I mean, we can talk later about this, and it is certainly related to the circulation. Whether it is, the relative storm, the internal circulation of the environmental wind shear, probably it's not that certain. This is, of course, there is a level of interpretation in this. This was mainly to show that this when you observe, normally the other increases with C, but in some cases, okay, I have here a plot. So you have this is the typical behavior in the mature stage, the mature region of the storm. When you see these large discrepancies, one explanation is that size sorting, for example, and it could be useful as an indication of the initial stage of the development. But yes, the actual cases actually can be more complex than this.
Yeah, thank you.
I have an online question, sir. It's a question by Uday Kumar Sahu. It's not related to this, but what would be the typical range of KDP for S, C, and X-band radar?
The typical KDP scales with frequency.
Yeah.
Yes, so if you have 1 degree KDP at the S-band, so you take the ratio of the frequency for C-band, you have 5, it's approximately a factor of 2, you will have 1.8 probably KDP at the C-band, and the ratio of 3 for X-band, you will have 3 to 4 degree per kilometer at X-band. So since it is a phase measurements, the KDP precisely scales with frequency. So you take the ratio of the frequency and you get the values at other frequencies. I mean, until X-band. Then there are too many miscatering effects that things may change. But in general, this is that's the rule.
Spiky measurements are good with the high frequency.
Sorry?
The same question. If you are increasing the frequency, is it better?
No, at some point it's not useful anymore. No?
It's up to 14 gigahertz.
Yeah, it's up to for the KU band. Then for miscatering, you use this behavior. It's not used at higher frequency.
So what's the, means like KU band, you are going for like smaller antenna or what's the reason? Just.
No, okay, man, it is, that's the system.
GTL.
That's the system, the space system had. So we had to make something similar on the ground. But then immediately people think KU is fashionable, but KU, X-band, it's all pretty close. Okay, X-band, the technology is cheaper, cost-wise.
So there is no other advantage.
slightly more, but it's little smaller, more attenuation. Advantage is too hard to sell. Oh, you big hand money.
Dr. Renzo for a commentative and interactive session. We have break for a small tea break. Reception back by 11:30. Tea is being served at the reception. And for another announcement, we have a photo selfie booth set up right outside the auditorium for this.
itself. And if anyone having a waiting list ticket, please submit a copy to the reception. And for further doubts, feel free to approach the desk. So now we are moving on to the next lecture of the day based on rainfall estimation and attenuation correction. For that, I welcome Dr. Luca Baldini to the stage. So welcome.
And the presentation is it is better to use yes. This is online. So, no, this is mine. This is later. It's trying. Yes. Yeah, but okay. Okay. Good morning. This is the second talk of this morning, and my name is Luca Baldini. I am a researcher at the Institute of Atmospheric Science and Climate of the National Research Council. I am used to cooperate with Chandra since a long time without numerical details because it's too long. So, and I'm happy to give this lecture on the Sub-Saharan rainfall estimation and attenuation correction. And let me, yesterday during the discussion, there was somebody who said, do radars measure precipitation? Do estimate? This is actually we are working with remote sensing. So what we measure is just the signal, the received signal, and we try to do our best from the properties of the received signal. And so we use this kind of abbreviation QPE that stands for quantitative precipitation estimation. So it is an estimation, it's not a measurement, but it's clear that is what the goal of weather radar is to provide quantitative measurements, not just to say it rains, it doesn't rain, but how much does it rain? This is maybe the most popular, I found my glasses first. This is maybe the most popular application of weather radar because, yeah, basically
radar, if you start studying weather radar, the first application and the most popular application is to measure precipitation, especially rainfall. But I want to tell you a story about an old physicist, an old Italian atmospheric physicist, who told me that we do something wrong because you can obtain so much information from radar, especially for meteorologists, because weather radar are also called meteorological radar. But what we try to do with QP is something that is more related to hydrology. And basically, according to this guy, we are wasting time because there is no way to provide a very accurate precipitation with radar. But I don't know if he was right or not. But let's see what we can get from our radar. So first, the talk is organized in this way. We start from single polarization, then dual polarization techniques, something more practical. We have now we know everybody that maybe at the S band we can neglect the attenuation effect, but with its attenuation effect with increasing when the frequency of the radar increases, so C band, X band, and so on. And then finally the blended algorithm that will be introduced later. So let's start with the classical approach with the single polarization. So we measure reflectivity or equivalent reflectivity factor, and we try to, with a simple power law, to estimate precipitation. So fortunately, we have seen a lot of this stuff before, or thanks to the lecture of Renzo and the lectures of Chandra yesterday. So we know what we call reflectivity. Reflectivity is the sum of the backscattering cross section of all the scatters, raindrops in the resolution volume delimited by the duration of the pulse and the beamwidth. So we got an expression like this that expresses the power received, and is not exactly the same formula I used yesterday, but it's equivalent. So if we work on this expression with two assumptions that are very important, so that reflectivity is a uniform in the volume and in the resolution volume, and if we have a Gaussian shaded beam, we can resort to this approximation, and we get this equation, where this is the reflectivity, which is the target of our measurement, because we want to estimate a geophysical variable. This is the received power. This is something that we are able to estimate from what we measure, so the sample of the received signal. And all these, yes, this is red on. Okay, all these are characteristics of radar. So we're supposed to know the transmitted power, the antenna gain. We are able to measure the distance and so on. Theoretically, all these quantities are part of the radar equation that we examined yesterday during the recitation class. So we have seen all of this. So reflectivity is an average radar cross-section. So the dimension is a length at the square is a square length, but we usually try to normalize the reflectivity using the expression for Rayleigh-Gans scatter in rain. So we normalize this factor, which is the true definition of the reflectivity by this quantity, so that we have this this expression for this after normalization. So after normalization, what we call reflectivity factor, and often there is we get a bit confused between reflectivity, equivalent reflectivity factor, and reflectivity. They say most people say reflectivity using, let's say, context information to understand which is the reflectivity. So often the reflectivity factor is the sixth moment of the drop size distribution, which is almost true for all the sides at S-band, but not at other frequencies. But this is useful to understand the physics that is behind the rainfall estimation. This is a more general because we have the scattering cross section that is usually valid also in Rayleigh-Gans scatter, but also it take account also the scattering. So we call this Z equivalent reflectivity factor. The equivalent reflectivity factor is in general different from Z because they are equal only on under Rayleigh-Gans scattering hypothesis. But sometimes we need to simplify the thing to provide clear explanations. So we want to relate this reflectivity. Let's use this generic term to rainfall rate, because this is the target, the geophysical variable that we want to measure. So rainfall rate is a measure of intensity of rainfall. It is measured by calculating the amount of rain that falls to the Earth's surface per unit area and the unit of time. We can develop the expression for, I don't know, it's possible to, I don't know, okay. So I typically want to use all the space for the slide. So, and typically the final information is at the bottom of the slide. So actually the amount of rain is computed considering the terminal velocity. The terminal velocity is something that was set in 1949. So very old experiment made with two circles that produced two spots, and but what is nice is that further experiment more or less confirmed this measurement made long time ago. So that we use. So there are some in this plot. There are Gann-Kintzer data, and there are so many approximations. There are also Renzo presented the further one. So maybe this one is maybe the more accurate, but for didactical purposes, it's nice to use this because it is expressed. It expresses the terminal velocity in terms of power law, and it is possible to develop this expression, and we see that rainfall rate can be considered the 3.67 moment of drop size distribution, while reflectivity is 6 moments. And of course, we use the behavior of drops falling is, let's say, follow the two curves only for drops no less than the diameter smaller than 3 millimeters, then the two diverges, and terminal drop velocity is almost constant for drops larger than 4 millimeters. So basically, we have 6 moment. Yeah, so these are two expression. I think it's the third time that you see this two cubes. So if so
it's very important.
yes, it's very important. So 3 times. So you think this is take away lesson. So something should be kept in mind. So we have 2 moments. Reflectivity is 6 moment of drop size distribution. R is D.3.67 moment. So in this figure, we have a fixed 37 dBz for reflectivity, and the same reflectivity can be achieved with a different drop size distribution. So 1 millimeter in this model is basically we have a volume filled with drops of the same size, and we get a rainfall rate of 35.6 millimeters per hour. We have the same reflectivity for again mono dispersed drop size distribution with 2 millimeter drops, and the rainfall rate is very different. These are further examples. This is 1 millimeter, 1/4 millimeter drop, and this is with a more complex exponential. So exponential drop size distribution. So what is clear here is that there is so the drop size distribution plays a very important role because so we can approximate the relation between Z and R as much as better than we want, but we have a variability of drop size distribution that depends on many factors, physical processes, and so on. So there will be still an uncertainty in these relations. So what we will use to demonstrate some important properties is the simplest distribution. Yes. So sometimes we will use the simplest distribution, drop size distribution, because this is very simple because it is an exponential distribution, but the intercept is fixed. So basically, it depends on a single parameter that is the rainfall intensity. This is called the Marshall-Palmer drop size distribution, and even this was derived long time ago in 1948 without using radar, without using this thermometer, but just piece of papers. So, but this is a fundamental experiment for all the radar meteorologists. In if we adopt this distribution, we will get this power law relation. So with two parameters. So and it is represented by this curve, and it is compared with I think they are from next slide. Yeah, that is the oh yes, next the relation. One is for cold season, so when stratiform precipitation relates. And the other one is for summer deep convection. So if we look at the what we get is quite different. And to apply this, there are many ways to optimize these relationships, but nevertheless they will bring some uncertainties related to the prevailing drop size, the distribution, the drop size variability. So this is the simulation, just to understand the uncertainty. This is simulations from using a drop size distribution measurements in the IFROS campaign. It was an important campaign, important because it rains quite a lot during a campaign, which is not very common. And they installed several hydrometers for two video hydrometers and also laser hydrometers. And computing ZH and rainfall rate, we got this approximation. But if we look closely, we get the rainfall rate of 1 millimeter for a very wide range of reflectivity. Or looking in this direction, if we have 30 millimeters, for example, 30 dBz, the range of rainfall rate that we can obtain varies from 0.5 to, let's say, 5 millimeters. So, say, an order of magnitude. So we have to invent something that is not so much dependent on the variability of drop size distribution. And the solution is dual polarization. So this is so far we have seen the traditional approach, the limitation, and so let's skip to the step ahead, which is the use of dual polarization. Dual polarization physically for rainfall is based on the oblate shape of a rainfall, of raindrops. This is not a new slide. It's, you have already seen it, but to Word insist on this. So thanks to the theoretical modeling of Bird Chuang, and also that is also compliant with the video recording that we have seen. This is the most likely shape of raindrops with a flattened bottom that tends to be more flattened as the size increases. But for most of the application, for radar application, it is sufficient. The approximation as a spheroid. Oblate spheroid characterized by an axial ratio that is expressed here. This is what Weir Chuang found, and these are nowadays the most used for obtaining scattering simulation and for simulating radar parameters starting from drop size distributions. We have seen also these, but comments are a bit different because now most of people seems happy with the Chuang formulation, but the depth of shape of raindrops was a very active topic at the beginning, from the end of the 90s and the beginning of the new centuries, because originally first was the most popular was this two-packer beard, so a linear relationship where the small drops were exactly spherical, and then there was this linear relationship. But at the beginning, people realized that ZDR was not exactly as predicted. So more let's say non-linear shapes were suggested, and it seems that now Berde Chuang can fit most of the purposes. Nonetheless, when we will compute rainfall measurements starting from disrometer measurements that we are going to do in this afternoon.
Yeah, I have one question. Like, how much uncertainty will be there if we use that different relationship? Because
yes, I don't have the slides here, but during the age of the drop shape arguments, yes, there is an influence. For example, between there are two critical points. One is at the beginning, because for example, people realize that this approximation here did not work. But and the other is for large drop, because let's say the approximation of oblate spheroid that doesn't work so much, and then also difficult to measure. But but if we consider oscillation that are taken into account through the variability of Canting angle, and considering one of these non-linear drops, non-linear drop shape model like Beard and Chuang, it came out that let's say even in ZDR is more important than the variability of drop size distribution rather than this one, rather than this the choice of drop shape. So but it has an effect. So okay. Now
There's another question.
oh yeah, so
Sir, I have a question.
Answer the equation of the axis ratio and the diameter, whether it changes for different seasons as well as in different places and different types of rain, whether that's relationship.
Let's say we are is more or less like the terminal velocity. Terminal velocity is depends on balance between gravitation, buoyancy, and other. And this is quite similar. So is is more physically based than climatology based. So I don't think, of course, if you compute, if you start from hydrometer data set, and you use one of these relationship, you can get different ZDR values, but not because of this, because of you make an average simulating ZDR and so on. So the drop shape, for example, in a regime with stratiform rain, you will use this range. Otherwise, for more intense drops, more intense precipitation, you use this. But let's say there is something that could be, let's say, universally because it physically based. These two are terminal drops and blackness. So because they are very similar for the concept. Because if you look at this, you have a measure of raindrop diameter based on the axis ratio. For terminal velocity, you have so this is used in polarimetry for horizontal observation. Vice versa, if you look at your radar point, if you make your radar point upward, the same role is played by the vertical, by the terminal drop velocity, which give an indication of the relationship with the drop and diameter of drop and dot component of Doppler spectrum, that what you use to derive a drop side distribution from vertical quantum grid. So they shouldn't be too much influenced by conditions. Of course, during a storm, you can have, for example, updraft that modify. But let's say all these are in stagnant air, so that we take as a reference both axis ratio and terminal velocity. Terminal velocity is by definition in stagnant air, but if you have downdraft or updraft, you have size sorting and so on. But for reference, it is one. So dual polarization was already introduced by Chandra yesterday, and so the dual polarization with the schema that is almost universally adopted is a transmission of a wave polarized vertically and or horizontally that impact on a sphere with an oblate shape. So the behavior of the scattered or transmitted signal is influenced by this shape of the raindrops. Assistant? No, maybe. Okay. Okay, this was a similar slide that was in the Chandra's presentation. So if for a single polarization everything is solved by the scattering cross section, we need 4 elements of a matrix that is the scattering matrix, and this is basically for a single scattering. scattering all this information is in these 4 parameters. We are not to measure everything with radar. There are many schemes of dual polarization radar, but the most popular one are these 2. One is alternate polarization that transmit one pulse in H polarization, and the other 2 vertical polarization, switching from a polarization to another. This was the first scheme of meteorological dual polarization radar that now is only used in research radar for now especially for operational application. What is more popular is the scheme in which the 2 polarizations are transmitted together instead of using the switch. This was actually in the very old configuration. There was also a switch on sometimes on receptions, but what typically they use the same circulator to get the copolar components of the system. So in these 2 schemes, in the alternate scheme of polarization, we can make this matrix of measurements. The first is we have to read if we look at these subscripts, we have the H means transmit H and receive H. This is transmit H and receive V. So the cross polar component. So with this radar, we have these 4 measurements. So all the parameters of the scattering matrix in theory can be determined. But while with this transmission, the most popular one that use a slant limb transmission polarization in transmission, we got in theory only copolar measurements. This is a loss of information, of course, but the implementation is more practical. So, but we can obtain many information also from this configuration. So this is a bit scary as a slide, because if what we have seen with scattering matrix is related to a single drop. But if we want to have an ensemble of drops, we have to use these are the, let's say, the covariance matrix of measurements that can be related to the properties of averaged scattering matrix. The formulation is quite complicated, but after all, what link the theoretical formulation with measurements are these equations. So in both schemes, we can get copolar measurements that we obtain with taking this component of the covariance matrix, and we have the amplitude of scattering matrix. The same we can do for vertical polarization and for the cross polar term. We cannot have this if we use the slanted transmission, because we cannot derive the copolar terms. And the final is this is called correlation coefficient. Copolar correlation coefficient is the correlation coefficient with the two time series of signal at H polarization and D polarization. This can be computed also with let's say the star or STR configuration. So this is the list of the measurements that we can obtain from a dual polarization, radar. So the reflectivity factor at H polarization, ZDR. So I don't want to insist too much on this. And LDR is a linear depolarization ratio, but you need alternate transmission radar. So most radar, you cannot measure this. The copolar correlation coefficient and differential phase shift, which is used for the copolar correlation coefficient is used for classification, while differential phase shift is used both for repolarization and attenuation correction. From differential phase shift, we can compute after a derivative the specific differential phase shift, but we will explain better later. So for rainfall estimation, basically we need to consider dual polarization and differential phase shift or specific differential phase shift. So we have discussed a lot of this on this plot that show the effect of that compare with the Rayleigh scattering, the effect that of a misscattering at C-band and X-band. So this is a summary of the oblate what we have, which kind of ZDR we can obtain for different shape of raindrops. So we are at S-band, so we can get a value between 1.5 dB, 6 dB, and so on. The discrimination of hail comes from the fact that hail is supposed to be tumbling and so on. But this is not the subject of this presentation. But to understand why ZDR is important for rainfall estimation, we consider this exponential drop size distribution, and we compute ZDR from as a ratio of reflectivities. This is a formula that we have seen before, and if we use this exponential distribution, it came out that these two terms that are constant and zero, they can be eliminated. So at the end, we have that ZDR that depends only on the mass weight, the median volume diameter of mass weighted diameter. So if our optimistic ZDR is a measurement of a drop. So the link between we started from a relationship with between drop size, drop diameter, and axis ratio. Translating this formula into radar measurement, we have this relationship, which is not so, let's say, so precise as the one that comes from microphysics, but we can see that we can say that the ZDR in practice give an indication of this these two important properties of drop side distribution. So it is independent on drop concentration. This is we have already seen this this morning. Skip this. We have seen also this because if we consider the different bands, yes, we still have the relationship between ZDR and D0, the drop median diameter of drop side distribution. But the shape changes a bit using different bands because you have a different response to misscattering effect. So again, for the average of this effect, S band and X band looks quite similar, and C band is the most pronounced for ZDR measurements, and KU is quite similar to X band. So these scatter plots are derived using two different shape model. One is Burton-Chang and the other is Brans. So you see that some difference is there, not that much, but to make a difference using one relation rather than the other. But they say it's not the most important factor for this. So let's take again so we have seen this scatter plot taken from IFOS campaign, computing R and reflectivity from this diameter measurement, as we see this uncertainty. But if we certify this scatter plot according to two different, this is dm, so mass weighted diameter, but it is the same with the median drop diameter. You see that this scatter plot follow more or less the same slope, but the intercept will be different. So this suggests that if we know the median drop diameter or whatever, we can reduce the variability with respect to drop size distribution. So, and we see that we use the same intercept. We see that the variability is not very well accounted for. But we would like to have this different approximation, this linear fit with more or less the same slope and different intercept. So what we have to do is to use ZDR for infer this information. So this is an example at the S band of horizontal and vertical reflectivity. Apparently, they look the same. Vertical reflectivity, we are at the S band, is just a bit lower than horizontal reflectivity. But if we compare horizontal reflectivity and differential reflectivity, we see a lot of differences that are not revealed by comparing the maps at the issue polarization. So, for example, we have a region in which we have high concentration of high value of the differential reflectivity, while here is low. So it means an area with high with the presence of large drops. The same something similar happens here. You have even here the prevailing presence of large drops. So basically, there is much more information on ZDR that are used for meteorological interpretation of images rather than the evaluation of estimation of precipitation. So the other parameter, the other measurement is the differential phase. It is actually composed between of two parts. One is the good part that we have to use, and this is the, let's call the bad part that is not because differential phase shift is a propagation parameter. But when we try to estimate this propagation parameter from the received signal, we have that this is somehow contaminated by these terms that comes from the scattering. But let's say we can create a test band. It can be significant in some cases that the C band, but so far we can estimate this correct, but at the moment we can neglect it. This is also shown this morning. This is a physical interpretation of differential phase shift. If the H and the polarized waves propagate in the medium with the spherical particles like drizzle, both of them have the same delay, so we don't have VDP, we don't have KDP, which is the derivative. So, and we have if the wave propagates through or narrow field with ovate particles, like in rain, the delay of the waves are different, and due to the fact that the behavior of ovate particle is different. The behavior used by ovate particle it depends on polarization. In rain, VDP should always increase. To be honest, that not always happen because there could be some alignment. So there could be effects of non-uniform beam filling, but typically we have increasing. We have this kind of behavior with monotonic increase PDP. This is of course this is too smooth because this is a simulation. Is not a measurement, but this is to show that from this this is the profile that we obtain. We can take a derivative, which is not easy because profile are not smoothed like this. And from the derivative, one half of the range derivative is the KDP. KDP is expressed by from this formula that was explained by Renzo. So I don't want to insist on this, but for what is important for us is that it has been demonstrated that for rain, KDP is closer to the fourth moment of drop side distribution. So considering that KDP is the fourth moment of drop size distribution and the rainfall somehow is the moment order 3.67, you see they are not so distant. So it means that algorithm relationship based on KDP should be quite similar. So there could be even a linear relationship between KDP and the rainfall rate. And we will see that this is what really happens. So this is the real motivation of using the KDP for one of the motivation, because it's not the most important one. I need to say a very important thing for that is important for comment this. So differential phase shift is we are able to measure it from the received power, but is estimation of a property related to propagation. Propagation means that also is a phase measurements. So there is no need to have one of the, if you consider reflectivity, differential reflectivity, you need to be sure that the received power is perfectly calibrated. So you need to know everything. You need to estimate with high accuracy all the parameters of the radar equation and so on. It's a bit easier for ZDR because it's a differential measurement that you can also apply some end-to-end calibration methods like looking vertically or so on. In this case, this is a propagation parameter. So it's not, for example, affected by attenuation, but we will see later, but it's not affected by calibration of the power, the calibration of received power. So this is a real FDP that with the noise added. FDP is considering the scaling with the frequency. It is let's say some properties are the same for all the frequency, but we consider the scaling for the frequency. If we say KDP scales with frequency, it means that if the radar system have a higher increase, have a higher frequency, the scaling is so that we measure larger reflectivity, larger PDP and the KDP. And this is so it means that the higher frequency system have higher sensitivity to the phase shift. So in practice, if we have an X-band system, it's easier to compute KDP from FDP rather than S-band system, because this delta FDP is scales with the frequency, so increase if the frequency of the system is a scale for with the ratio between the two frequencies. So how can we use these two information, so ZDR and KDP for rainfall estimation? We came here. We arrived to this equation, and it's missing. Okay, is it? So what we would like to have, we saw that if we know the mean drop diameter of the DSD, we can have a more precise approximation of the scatter plot. So basically, but instead we use this kind of approximated relation. We can establish algorithm using dynamometer and electromagnetic measurements, and but I think it's better to write this relation in this equivalent form that is well explained by this graph. So it's like this part of the equation estimate dm that modify the intercept of this slope, and the slope of this intercept of this linear fitting is related to b. So you see that the b is not varying that much for different frequencies, and somehow this term adjusts the ZR relationship for the prevailing diameters in the drop side distribution.
Yeah, I have one question. Like this is based on the dynamometer observations, and what we have learned that your CDR is a function of again e to the power 6, like you have shown. So because this radar equation is again applicable for that dynamometer location, but radar is looking at the different topography and other kind of the things. So how do you think we can optimize this algorithm? Because it is again another form of like CR relations, but with more precise measurement, but applicable to that location. But radar is looking at the different topography, maybe sometime over oceans. And so any thought like how to do that kind of the process so that minimize the error?
No, there is a of course, if you take two dynamometers located in different climate region, you will see a difference, but not such as great like in the relationship, because what the point is the rationale is to try to estimate this, to estimate the DM real time, because it's in the property of the measurement, that make this measurement more less location dependent. Of course, if you apply to try to apply, but it could be a good suggestion for the next for future recitation. So look at the different dynamometers and look at the variability of the different. So of course, if you do simulation, you will find variability, but not as high as in for ZH. So the other, if we talk about dynamometers, we can talk, because sometimes we make not a mistake, but we consider ground measurements as the ground truth. Yeah, because of course radar are not perfect, but neither rain gauges, neither dynamometers are perfect. So if you estimate something with these barometers and then you apply to radar and then your barometers doesn't work well, they are short propagates. So we should be very careful about this barometer. So this is the estimation with the KDP. KDP is used as with a power law, we can even use the same exponent for all the frequency and the different value of C are due to the scaling frequency. Basically, the equation is the same, but it is just scaled with the frequency. We can also improve this using the KDP and ZDR. Theoretically, we have some improvement, but this is the real question. We don't like ZH because we prefer polarimetry. But yes, we have derived all things using these barometer measurements. So we rely on the barometer, on simulations. So we forget about measurement errors. Measurement errors are not the thermal noise. It's due to the fact that the drops change position from one pulse to the other. So the scattering is influenced by the change of the position of or from one pulse to the other for different position of the drops. So we can, this variability is called, no, I was anticipating it. So this is sorry. This is a comparison with these barometers of ZH and a parameterization that uses also ZDR. So there is no, this is game over. This is much more better, much better than the dual polarization overwhelm the performance of a single polarization. But there are measurement error because these measurements are obtained from the power received from a number of pulses. If we take, for example, if we measure reflectivity with a single from a single pulse, from one pulse to the other, the variability is 5.57 dB, so quite high for rainfall estimation. This is deduced by averaging. And if we add some realistic measurement error, somehow the advantage of using ZDR is not as it was before. So let's keep to, if we consider sorry. Okay. If we consider KDP is this is theoretical. This is the advantage of this is the scatter plot of simulated KDP and R. So this is the same thing that we obtain with using KDP and ZDR. ZDR, the role is the same. Estimate the DM and reduce the variability to the variability of ZDR. And but if we consider that, especially in this case, if we consider the measurements errors, and so the variability is not that high. So at the moment,
what are the factors will come in that measurement error?
The measurement errors, in KD for GH theoretically depends on the correlation, the width of the velocity spectrum. In ZBR, width of velocity spectrum and copolar correlation coefficient. In KDP, and also you can decrease or increase using different number of integrated pulses. In KDP, you are computing a derivative of a noisy profile. So it's a very risky. Operation. There are methods to minimize the error, but you always take it's like yes, it is a filtering, but you compute a derivative. So
because this is from thematic simulations.
Thematic simulation and added an error component.
Because that is an ideal simulation, so how this measurement error will come in that simulations?
Okay, so it's actually, yes, the simulation with the thematics, and then we added standard deviation to the observation to simulate measurement error. The standard deviation of 1 dB for reflectivity, 0.1 dB for CDR, and 0.25 degree per kilometer for KDP.
Also, you introduce
this error artificially to simulate the effect of the measurement error on top of the parameterization error. So this is to show that without measurement errors, of course, you have better estimates. With measurement error, it depends. Depends how you are able to keep this measurement error.
This is an example of measurement errors because, for example, in if you use the 1 dB for the variability. Yeah.
Thank you.
So, so far we have considered this measurement error, but since we are interested also in using the C-band and when I should finish.
Yeah, it's 1 o'clock, we have lunch time.
So is it 1 or 1:30?
1.
1. Okay, we say 1, and negotiate 1:10.
Yeah.
I'm sorry, I know that. This is why nobody's asking questions because there's a lot of more questions in lunch. Attenuation. First, we have talked about scattering in ideal situation in which attenuation is not present. But of course, wave that propagated into medium are attenuated. Attenuation is composed by absorption and scattering. Absorption is a loss for the energy absorbed by the rocks and converted in heat, and scattering is the energy scattered in the other direction than the backscattering direction. So the one that is interested for us. So there is not only attenuation from raindrops, but there is also from gas and water vapor that we can neglect up to X band and maybe KU band. For example, if you look at GPM global frequency radar, they use the KU and the KA. KA is corrected for water vapor, but not but they don't correct K band for this. So another thing is that absorption dominate up to expand. We talked yesterday, Professor Chandra talked about this yesterday. Is dominated for the traditional frequency for scanning weather radar, so up to expand. We can focus on absorption. There are of course, we know that attenuation becomes much more important if the frequency increases. So these are simulation of a normalized extinction cross section. It is normalized by the geometrical area of the drop. We see that this extinction cross section increases as the diameter of the drop increases and as the frequency of the radar increases. It depends on the temperature. Up to Ka band, colder are the temperature and the higher is the attenuation. The opposite is happens with the W band, and you see even for large drops you have something that like remind misscattering. So this is how we compute, how we use this information. So what we saw is the extinction cross section, but we are interested in attenuation. This was for a single drop. If we take an example of a sample of drop, we need to consider drop size distribution and average the single extinction area section with drop size distribution. And we use this formulation that express the specific attenuation in dB over kilometer. Again, these are simulations based with a Marshall-Palmer drop size distribution, the nice one that depends only on rain. So we get this again, this dependency on frequency and this dependency on temperature for different rainfall rates. So same, of course, there is a different attenuation for different polarization, and of course, attenuation for H polarized wave is larger than for depolarized wave. Is like scattering. This is due to the oblateness. Again, there is a scaling with the frequency and dependency on temperature. What happens in practice? This is this figure shows two different profiles of intrinsic reflectivity. So what we have from the hydrometer simulation, but from the hydrometer simulation we can also simulate specific attenuation. This is S band. This is the intrinsic, and this is the effect of attenuation. This is the cumulative attenuation that is called PIA, so path integrated attenuation. That at S band, this is a quite long and intense cell. It can arrive to a few units of dB. This is C band for the same cell. The difference between observed and the intrinsic is something very high that need to be correct. So we want to get C band. We want to get rainfall estimation for using reflectivity. So fortunately, we are able to measure a propagation. With the dual polarization radar, we are able to obtain a propagation parameter. This propagation parameter is KDP, and we can see here that there could be established a relationship between KDP and the specific attenuation. This is shown at H polarization, but it exists also at for the differential for differential attenuation, and so we can obtain some an estimation of attenuation using a parameterization that is essentially linear with KDP. So since KDP is computed through the derivative, which is a dangerous, is a tricky operation. The alternative is to use the path integrated attenuation estimated from PDP and use ZDR. There is a mathematical formulation that somehow distributed this profile here is of attenuation of total phase shift. It is distributed according to the measurement of reflectivity to obtain a profile of specific attenuation, from which it's possible to correct the reflectivity. So this is what we can do for when we are working at attenuated frequency in order to get rid of attenuation problem. We can use ZR and ZDR and try to correct ZH and ZDR using KDP, or using directly KDP, because KDP is not affected by attenuation. There is no problem with attenuation effect, no calibration effect, and also we can use CH and KDP using this integrated path correction. So some example. These are observations from Renzo and Roberto's radar. This is a case from 2006. So these is what we see in horizontal reflectivity. This is ZDR. You see that, for example, here you have some attenuation, evident attenuation effect. You have a crater around, and this is PDP. You see this increase, and you see these changes between positive and the negative. This is due to the folding. There is a limit in the measurement of PDP that is established by the maximum unambiguous range of Doppler, but we haven't talked about this. And so basically we have first to clean this PPI from noise and clean this from folding effect. We have this, we take the derivative, and with KDP, this is what we obtain. Of course, what is clear that during some filtering we lose some information, some decays precipitation. But if we look at this shape and this shape, they look quite different because what is the problem? KDP is not affected by attenuation. So if you look at this rear part of the cell, this is it disappears from ZH that is not corrected. So typically, if we look at the shape of many intense cells at the C band, we see this strange shape as an arc, but this is just an effect of attenuation. If we compute KDP or we fix attenuation on the ZH, the shape is different. So if we consider the same cell, it is observed with a negative elevation, which is common if your radar is on the top of a hill. You want to measure precipitation as close as possible to the surface. So spot is one of the strategies is to use a negative elevation. So this is on the right. We have estimation with single polarization ZH. This is with KDP. Results are quite different for this elevation, and these are from comparison with the rainbow gauges. So correlation coefficient is decent with also with ZH, but from a point of view of the error in estimation, KDP is doing well, but while single polarization estimation underestimate. There is a reason for this, because this is the scanning strategy. The lowest elevation is minus 0.3, then is 0 plus 3. So we go to positive elevation. So looking with elevation angle lower than 0, one of the problems can be the intersection of mountains, and this is what happens. Because this is another form of say attenuation, because the beam is partially screened. So the part of the power that propagates beyond this obstacle is less than the one that was here. So this explains why we have this very strong attenuation.
Yeah, what you said, I agree. Suppose in one rain event, you have underestimation of like 30 mm. This is like, I can understand this is very well calibrated, and still we got an underestimation of like 30 mm. And this is for, I think, one event.
Yes, this is one event that is didactical.
So can you make some suggestion? So how to come? Because if you consider like for India, entire monsoon, so radar will always show underestimation kind of the things, like 30 mm for one rain event, maybe other rain events, it will become like cumulative. So because we observe this kind of the phenomena.
Yes.
So what will be your suggestion so that it should match with any ground-based measurement, or we should come up with like whatever we are observing, we have to deal with that one, or what will be your suggestion?
Suggestion, I think it's one of the topics of Roberto tomorrow. It's one of estimation in complex orography, but for sure, lost connection maybe.
Thank you so
much. Finally, somebody is going to voice. I try to speak loud. So typically, if you are using only Okay.
Use this one.
If you are using only horizontal reflectivity, of course you have this kind of effect. But you can mitigate this using KDP because it's not easy insensitive to this unless the signal is not distincted, which can be the case. But this is what you can do. But try to estimate precipitation in a complex environment is not that easy because you have to ideally you should be your beam should stay closer as possible to the but you have to increase the elevation if you want to pass the nearby obstacles and okay. And so you have to use a proper scanning strategy, optimize the location of the radar, which is not so easy. It's easy to do on the map, but not in practice. And use, for example, these parameters that is not affected by attenuation. And of course, then I started problem with vertical gradients. And so on. You have a downdraft. So imagine I'm not expert of monsoon. We have a lot of convection activity in Italy, and the problem is always there. So
yeah, so like 30 mm of under. So will you suggest like
we should go for like, that is the reason some people do like radar and gauge product to make up like that way. So is
yeah, it's even let's say it's a case that could work well because if you have attenuation, you have an A attenuation that you don't know very well how to deal with in a very complex situation in which your beam is screened by a very high percentage of the beam. Even ground measurements can help. But no, if and also using surface information to derive rainfall estimation has become again in fashion because of machine learning. But even there are methods that you can. But if you use rather based information, it's better to use information that is not affected by blockage. This is but in the mountain you have cut, so you have. It's not so easy. Maybe yeah. What is
the last slide for lunch?
Yeah, I can skip to the last information
because this is a well-full topic. We can jump in. We can talk about this for next 2 hours. No, it's okay. And I was about to jump in, but then I said, look at all these people feeling hungry. So why don't we finish this? We come back to this because I want to liven it up. Because when they come back from lunch, they will be half sleeping. Yeah. So at that time we can debate vigorously about this.
okay.
Okay. So I will skip this example of the rise.
Everything has an opinion on this topic.
Yeah. No, they all just to illustrate quickly 2 slides. So there are methods that combine ZH estimation with KDP estimation. So typically KDP is used for intense rain and single reflectivity measurements. ZR relation is used for low intensity. So there is an example, let's say, in which making a use of the best of the two relationship, the one with CH and the one with KD2, we can obtain some measurements. But this is what we expect. Take the best from these two. Not always the results is warranted, but this is what was obtained. So, sorry for, I think I spent too much time at the beginning. So, for any questions later, or later, or? Okay.
It's okay.
Two questions, right?
So I have a doubt regarding these relationships which we have, which I shown. So, like, is there any study which has compared the temporal validity of these relationships? For example, if we have with increasing temporal scale, windows,
You made this one, huh?
the RKDP relationships and the RZX relationships.
You know, I want to put his question in context because this is very important. He's a hydrologist. And so.
No, they say this, you say hydrologist is a.
No, but I'm trying to see, they want an engineering solution and a clean, he wants an engineering solution and a clean formula. Whereas the problem with meteorologists is they will talk for 3 hours, how the raindrops evolved, how it went here, how it went there, how it oscillated. They get very excited about all this, but hydrologists need a number.
Yeah.
And he wants to know, can I use this formula? Will it work? And then will it change the time? That's what he means by temporal.
Okay.
So I think when we communicate this is with the hydrologist, we have to turn off our meteorologist thinking and see how excited about physics applied these things and give a clean solution. And so we will talk about all this, I think. I don't know, what's the topic after lunch? What's the topic? Renzo, what's the topic after lunch? Oh, you're talking?
Yeah.
Oh, actually, that's very good. After he finishes, we can have a good discussion because he is a card-carrying hydrologist, as I call him. And I know his professor. He's even harder hydrologist. Right? Okay. Yeah. So I think we need to keep that in mind because in the morning, we got, because we are in IITM, we got swamped too much by meteorology and physics. We want a clean formula.
Yeah. Maybe during my presentation also I'll talk about it. Now with the increase in this extreme events, especially our cities which are very much congested, we have very limited options for flood mitigation measures. So forecasting or early warning, these have become very, very important. And for that, we need rainfall data. That is our primary input for forecasting system. So
we mean hydrological forecasting?
Yeah, hydrological.
Yes, yes.
So like rainfall rate, millimeter for this interval, and spatially and temporally.
Yeah.
That should go as input in our model, and then we'll do other things. And the accuracy, we have rain gauge system, that old engineering system, but rain gauge, we are seeing that over the time, it may not be that accurate. A radar can replace that thing, or something means we can get in a better way.
Well, what is the
Rain gauge? Rain gauge is like, it is like physical instrument.
No, I know what is a rain gauge, but how sparse are your rain gauge?
Rain gauge have two spots in India, like, let's say Chennai, we have Adia based, one basin is there. It's about 900 square kilometer. We have hardly 4 or 5 rain gauges. Okay, with that itself, we are doing everything, but that is not, that's giving some idea, but you cannot like give warning like you evacuate your house. But we need that information.
Yeah.
You know, I am violating my own rule, holding everybody from lunch. But I want to say something exciting so that it's not too boring. So there was this, there's this big NASA program called GPM, Global Precipitation Measurement. So that's, again, so one of the things was everybody who had a rain gauge. It doesn't take much to get a rain gauge. They compared with the GPM's rainfall. And that doesn't compare well. Immediately they write to them saying NASA's rainfall is all wrong. And this is okay, I can say that. But then they ask them, how do you use your rain gauge correct? I think so, I don't know. I've been using this for a long time. Then some NASA people, what they did, you put 3 rain gauges at the same place. 2 out of the 3 rain gauges have to agree with each other. If they are not agreeing, you have no business of comparing with me. So when they did that, 90% of the rain gauges have to be thrown away. So this is one problem with, I don't want to say that. I don't like the people using rain gauges because it's such an easy instrument. They believe in that too much. It's true. So I have a personal experience. So after this, I will stop. I ran a big network in the city of Dallas, Fort Worth. I keep tell this story to everybody. So how should I do that? Let's say let's make a partition. This side of let's say you said Andheri, right? There is a boundary. This side of Andheri is one district. That side of Andheri is another district. Okay. And in Dallas Fort Worth, I'm comparing radar rainfall with gauges. It doesn't agree. So what they asked me to do is, okay, but we like your radar because it gives spatial coverage, but you are giving yours is 70%. So adjust everything 70% up. So we will use that data. I said, you say that it's 70% off. I have to go check something in the radar to make the adjustment of 70% to be wrong. I can't just blindly change it. So I was very uncomfortable, and then somebody saw me uncomfortable in the meeting, and they told me, okay, go talk to the next city. The next city, they have a very good rain gauge network. It's maintained well. Their staff is very good. So I just went on this side of the street and got all their rain gauges, and it just matched perfectly. Whereas this side, which is a big city, the rain gauge contract was given as subcontractor to a subcontractor. Nobody cared. Some places you go, a tree has grown over the rain gauge. After the rain is over, it keeps dripping and rain goes on for a long time. Other places, it's like somebody has built a shed over the rain gauge. It's not even raining. And we take these rain gauges and feed it into models. So what we are trying to do is develop what is called as super sites, where these are calibration sites. And we take all the rain gauges, put 3 of them in one place. 2 out of the 3 have to agree with each other. Then we use that for comparison with radar. Then we are beating on the middle ground how to deal with. So it's 90% of the times, the problem is not science or engineering. It's very practical solutions. I think that's a good note You want to respond?
Yeah, means no, we agree with you because rain gauge measurement is influenced by many factors. Even if then also we get different measurement. So we are aware of that fact. We are aware of the limitation of satellite products. So that's why we are looking for alternative solution, and we think radar could be the one. And but again, then we go for another kind of validation. But you told like 3 rain gauges, 2 should agree. We can pick it up. Another validation is like measurement of river discharge, measurement of other things. So when we run the model, we go for second level of validation. From rainfall to runoff or some other things, again validation. So there also we can check whether my rainfall was correct or not.
No, rainfall was correct. The model was correct.
Yeah.
So many things.
So many things.
But that's very called.
Yeah.
Internally self-contained with hydrologists. But right in the interface, you should, myself and Lorenzo are struggling with a big project now where we produce rainfall rates and we are pulling each other in 2 different directions. And so it is, but fortunately or unfortunately, for all the people in this room, measurement of rainfall is one of the toughest problems. So when some of the students came to CSU, they thought in the shelf there is some formula. Here I get some data and then put it into something and run something and then immediately gets an answer. Right is done. If you go look back in the history, right from the period of before Christ or even our Chola kings, or if you go to Chinese, they have been trying to measure rainfall. We are still trying to measure rainfall. The reason is rainfall has a variability at all scales. It has variability at raindrop scale. It has variability at city scale. It has variability at street scale. And it has variability at state scale. Just because of that, it's one of the most difficult things to measure, which is good. If it's a solved problem, all of us have to find some new work to do.
Need to work.
So one way it is good. It's giving work for all of us.
What will be the effect of winds while estimating the rain rate using radar?
Effect of wind.
Or it's not automatic.
So now radar, there is no problem, but the gauge, if there is a wind going over and he knows some papers, the rain gauge only collect the rain, will go away.
Any other questions? Okay, let's stand up the record.
Thank you. Thank you for your attention.
Now,
Good afternoon, everyone. Welcome back after the lunch. I hope we are ready for the next session of our workshop. I invite Dr. Somendra Kure, who will be delivering the next session on the topic Application of Radar Rainfall Product to High Resolution Urban Flood Simulation. Thank you.
If it is
So, good afternoon. Welcome to lunch. I hope you will not sleep. Again, this topic is a little different than what I've been hearing from yesterday, but these are all connected. And I especially, I'm very much interested in interdisciplinary work so that we can translate our thoughts and our scientific knowledge to the society. So if you look at the incidences in the last 10 or 15 years, in many Indian cities, flood has become very, very common. And if you look at like especially Chennai, I'm from IT Madras. So there also it's very, very frequent. Like we had flood in 2015. That was really in very, very high scale. In hydrology, we call it 1 in 100-year rainfall event. Okay. And then again, there was flood in 2020, 21. Again, it was in a bigger scale in 2023. Now, few things are happening. Sometimes flood will be just because of extreme rainfall and there is no other disturbances. Sometimes what happens during cyclonic time, Chennai city, it gets rainfall during northeast monsoon. That means during October to December. Now, what happens that time? There will be cyclone, and because of cyclone, there will be water level rise, storm surge will be there, and there will be huge rainfall on the land side. And through the Chennai city, there are few rivers. So because of heavy rain, there will be overflow. And on top of that, Chennai is a coastal city, so the slope is quite flat. So if there is rain, it will not go out so easily. Now, if there is high water tide, the ocean side, then there will be blockage, the city to the ocean. So this whole thing makes it very, very complicated. Now, what are the options for mitigating this situation? There are structural interventions, like we can go for more reservoirs, flood control reservoirs, especially in the upstream side. And another thing is in Chennai, there are many naturally replaced storage reservoirs or tanks. We can call it lake, but the local name is tank. Once they were very much connected, well maintained, but many of the lakes, they have lost their capacity because of siltation, and hydraulic connectivity is also getting lost because of rapid urbanization. Now, keeping all these in mind, what we are thinking that we can go for flood forecasting system. So let's say if we can give early warning at least 5 to 6 hours before the actual event, then we can reduce the damage substantially. If you remember in 2015, there was huge loss everywhere, from domestic to commercial to every sector. But surprisingly, in 2023, there was good rainfall forecast from IMD, and it was so good that people believed also, and many people beforehand they parked their cars on the streets, but streets are at high level, so it could reduce significant the damage. Now nowadays people are thinking the ground floor how to take care. So keeping all these things we can address with this kind of study, like application of high resolution rainfall product, which can come from radar, and that we can use for urban flood forecasting. Now, why I'm telling high resolution? I don't know that your scale is quite different, like in kilometers. But if we go for urban flood prediction, we should go for less than 10-meter resolution. Means some people are trying with 1 meter, 2 meter, because otherwise you cannot capture urban topographical features. Like we want to capture flow through the streets, rivers, drains, all these things. Then only it is urban flood. Okay, so in this session, what I will try to do is, I will not go into the mathematics behind it. I want to give you the flavor, means how we can use this rainfall product, what are the research scope, and where different communities can come together and address this problem jointly. So those things I will discuss. And my student, Baby Arita, she is working on this topic. She will be giving the demo of the one hydrological model. The purpose is you should know what are the parameters we are using. Not only rainfall, there are other meteorological parameters. Most probably we can get better data from meteorological side.
Hey, Sarika, stand up. Oh,
Right.
that is the one. Give it a-
Okay. So I was talking about some of the floods over the time, like 2015, 2013, 18, 23, and first two figures, you see it's almost the same area. If you look at the angle, and you see the change in urban that expansion. So that is also creating problem. Now, when you talk about flood, all floods are not of the same type. We cannot model them like in the same way. So we can classify it. One could be coastal flood. It's mainly because of storm surge. And then we have urban flood only in the urban area. It is part of fluvial and river flood, like fluvial flood. Fluvial flood means it's just because of rain. Because of heavy rain, there will be the surface water, drainage surcharge. It will be fluvial flood. Fluvial or river flood means there will be excessive river flow, then at some location it will overflow and it can inundate the city. And then we have flash flood. That is because of high intensity rainfall over a small area. And that can be more disastrous. So we'll focus on Chennai flood because we could get some data, radar data for Chennai, especially 2023 event. But the data is limited because we got only for 2 days. From the third day, it was not working because of local inundation. So during this cyclone, we call it Michang cyclone in 2023. There was heavy rain and then flood, huge loss. Now, if you look at this area, this side is Bay of Bengal. This we call it watershed in hydrological term. Okay, if there is rain, then water from this entire area will flow through this area. And this blue line, this is the main river, Adyar River. It's flowing through the Chennai city. Actual Chennai city is much larger than this. There are other basins, but the main CMA, Chennai metropolitan area, that is in this part. That's why we are considering this part. What happens if you look at the shape of this basin? If there is a rainfall over this basin, then this entire water, after filling all the tanks, these blue dots or polygons are lakes or tanks. And this is the major reservoir, Chimbermakam reservoir. That water is used for drinking water supply. So what happens? This entire water, this will flow to this side, it will join here, then it will flow through the city. And from Chimbarambakkam, if there is a release, then this water will come from here and it will join the river. So all water will go to the Ada river, and that river is flowing through the city, middle of the city. Okay. Now, this figure will give you a better idea of this basin boundary, and these are the stream networks. They all are not rivers, but the water will flow, see their path through these networks. So now we can come to the modeling side. So now when we go for hydrological modeling, it's a simple model, like it's water budgeting. How much rainfall is there, how much loss is there, and then how much flowing over the surface. That's the main crux of this hydrological model. And that's why we use mass conservation equation. That is the simple point. So if you look at this basin scale or watershed scale, then what are the major processes are there? So we have precipitation. This can be in different form, but in Chennai it's only rain. So that is a major input to our model. And this rain, it varies both spatially and temporally. And then there will be losses. So losses means, like, first loss is all kinds of buildings, vegetations are there. There will be interception loss. Then from the plants and other things, there will be evapotranspiration. Another kind of loss. Loss means with respect to budgeting water. And then part of that water will go below the surface. That we call infiltration. If it goes deeper, then we call it percolation. And some of the water will flow as groundwater. So that water may come out wherever there is a stream. We call it base flow. And then, so from this, then on the surface, what will happen? If there are reservoirs or some storage system, first it will fill them, and then it will start flowing. That remaining flow is called runoff. So now this all these things we will sum it up, and then we route it. That means through the streams means how much water is going to the neighboring lowest level, that will define one stream, hypothetical stream, and then part by part, finally it will join to the river, and then that will go to the ocean or some other system. So this is the background of hydrological model. So within the hydrological model, we are trying to model different processes. Each processes is again modeled by different types of theory. Like let's say evapotranspiration. We have a separate model for that. How evaporation is taking place. Infiltration. All these things are taken care separately, and then it will be combined together. How much water is going one point to the river, and then we do routing model. Routing means kinematic routing or some full dynamic routing. Is how at one place, let's say, water level is varying like this, then how it will translate and to the river stage. And there will be time delay. Sometimes in the river, if there is network system, it will go here and there, it may overflow, and remaining water will flow. So hydrological model, it will give you time versus flow curve at different location, or we call it distance, or stream flow. Now, earlier days, like before 90s, this used to be the flood warning system. So if there is a huge discharge, then there will be a prediction like it can overflow the river bank. So there is a flood means possibility. That was flood warning. And this is what we can do in hydrological model. And the best advantage of hydrological model is, since it is simple, we can use it for a very large scale. Like it can be like watershed scale to state level to even continental level. So this type of hydrological models is possible. However, with these models, we cannot predict the flood inundation pattern. Like what you are interested, like at what time, how much water level will be there near to my home, like on the street. So that we cannot get from hydrological model. So there we need hydraulic model. So hydraulic model means that model solves two sets of equations, mass conservation equation and momentum conservation equation. And here we get depth of flow and velocity. Okay, so that model gives you flood maps, hazard maps, and that will give you more insight on how to mitigate floods, like different types of interventions. If we want, let's say, to put another reservoir system or detention diversion channel or low impact development, all these things we can test one by one. Now, what we did for Chennai, for this particular thing, if we go back, yeah. So here, because this entire stretch you cannot consider in hydraulic model, because hydraulic model is computationally very, very intensive. So we first run hydrological model, and if there is no measurement somewhere in the river, we predict this stream flow pattern, time versus discharge. Then we forget about the hydrological model side. We focus wherever we need flood inundation dynamics, like over the city area. That smaller part we take for hydraulic model, and there we do very high resolution simulation. I hope this part is clear. I think in the back side little bit. Do you have any doubt?
No. River catchment. If there is any discharge, whether you need to consider that part also.
Yes. So when we run this hydraulic model, these models are called equations of initial value problems. So we should know what was the initial condition, means how much flow was going through initially. If we know that one, then with the initial and boundary condition, then we will automatically calculate how much water. So we should know the initial condition. After that, it will evolve.
Yeah, so then there should be like real-time informations from, like for Pune city, we have so many dams. Sometimes they release the water. And then it become like a school is holiday for next day.
Yeah.
Even there is no rain, but people will not understand the discharge.
Yeah, so let's say whatever dams are coming, let's say in this water state, we should know their release pattern. When we open the dam gates, it's not arbitrary. There are rule curves for that. They will follow exactly those rule curves. So they open the gate based on that thing. So we get this release pattern, and that release pattern will go as input in my model. And then that water automatically it will flow, combine, and then it will flow out. Yeah. Now, so far we were doing it in this way, like partly first hydrological model, then hydraulic model, and now why we are doing it? Because the main input, that rainfall, we did not have very high resolution data. Like in this entire basin, in this entire area basin, we have only 5 to 6 rain gauges, I think. 9 rain gauges. So just a minute. Yeah. So I don't know. There is a lag. Okay. So in entire this almost 900 square kilometer, we have only 9 rain gauges. So we cannot go for very accurate simulation. So we are looking for alternate measurement techniques. It can be satellite data, but again in satellite also there will be a lot of means with respect to rain gauge, we will get a lot of differences. That probability is there, but with IMERGE for many rainfall events, we are getting quite close measurement data. So what we do is, if we get, let's say, radar rainfall data, which is spatially distributed at higher resolution, then we run special type of model. We call it distributed model. So entire basin, there will be grid, one model, everywhere rainfall input will be there, and then we can simulate it. Okay. Yeah. So again, just to let you know what type of meteorological parameters also we are using. So if we focus on hydrological model, so it can be the topography, we can give it as input. It can be subwaterside or subbasin, and it can be polygon, triangle. So different models, they use different types of the definition. Like a distributed model, that definition is subgrid subbasin or polygon concept. And in each polygon, we'll be budgeting this hydrological cycle. So what are the major things in precipitation, evapotranspiration, and this will give me interception, this thing, then surface storage in the form of lakes and other things. Then part of this water will go down, infiltration, part of that will go for groundwater flow, percolation, and then this is, we call it routing. Now all this water, when it will flow to the river, then that flow will go to the next part. In this way, water from the whole watershed will start flowing, and that we do the modeling. That is the modeling part of this process. Now, what type of rainfall products we need? When you go for engineering solutions, we don't go just for the present moment, means what type of data I'm getting immediately, like radar rainfall data. It's like it's measuring online. So that is one thing. We need historical event data for engineering design. We need forecasted data to intervene, means what can be early warning system, mitigation measures, if there is evacuation plan. So we need past, present, future, depending upon the requirements. Okay. Now, so far, what is happening? We have been using rainfall data. Let's say last 75-year, 100-year rainfall data is there. Then we do some statistical analysis. We project it to the future. Then we come up with like probability kind of thing. 1 in 10-year rainfall. What is the intensity? And based on that, we design storm drainage system. 1 in 1,000 year, then we design one dam structure. We did not have this type of distributed data so far. Now it's coming. After 15, 20 or 30 years, and this data will accumulate, I think our thinking will totally change. We will not rely only on the point data. We'll go for the spatial variation, and then we'll look at it in a different way. And then again, the next thing is now we have data-driven models. So when we'll have huge amount data, past data, based on that we can learn and we can go for forecasting. So in that case, if you look at, so far we were relying here, now we are getting this type of data, which is spatial and temporally variable, and it has wide coverage. And if we have sufficient radars, we'll get very good coverage. So once we do the hydrological part, then we go for hydraulic modeling. So here we need some boundary conditions, like in this side we need tide condition. In this side we need this river discharge pattern. Then we need to go for model calibration validation, and then only we can rely on results. So when we try to use two different models, we have to run them sequentially. So first we go for hydrological model, and here the inputs are digital elevation model that will define the topography. Then land use, land cover map, LULC, that will give me the types of land, that the soil type. So then we have soil type. Soil type is for infiltration. Land is for another purpose like resistance and other things. And then we have precipitation and some meteorological parameters are there. They all will go into the hydrological model. Then we'll go for calibration validation. So here again, let's say if there is any discrepancy in my measurement in rainfall and other parameters, so we can check again here. When we go for hydrological model calibration, where we do hydrological model calibration, if we know reservoir release, from that we can get inflow data, and our model will predict inflow. That we can compare. We have water level variation or stream flow variation. So that is at second level, we can check how accurate was our other parameters. So finally, all hydraulic model, when we use it for one urban area, we try to get this type of simulation. Here we look. This we did for Chennai downstream. The animation is lagging here. So this is Aripuram area. So this is the main river here, and there is a turn like this, and then it goes out here, and there are many buildings here. So we try to get this type of flow pattern. So this gives me depth and velocity, and this can be used for like flood inundation forecasting and other things. So this was the background thing. Now next part is whatever radar data we have so far in our hand. We have tried to use it for 2023 rainfall event in Chennai. Again, the radar, there is only one radar, and that is located away from this our area. So it does not cover the entire basin. So IRC was trying to come up with some blending technique, radar rainfall, rain gauge, and we are trying to get good results. That part Arita will describe, and she will also give a small demo on the hydrological model. If you have any question from this part, you can ask me. Otherwise, she will take over.
The hydraulic model is very simple, and how do you select the domain where this hydraulic model is run?
Yeah. So for hydraulic model, we are going for let's say if it is urban flooding, our target area is the urban area. So where I need detailed inundation map, so that part will be my hydraulic domain. But again, sometimes what happens, you cannot exactly demarcate that area only. We have to extend it a little bit just to give boundary conditions and other things from the hydrological model. So in this case, only the downstream part I focused, but that may not be the case all the time. That's why we go for a simplified hydraulic model so that we can use it in larger scale.
The Chembalbakum series was there in 2015. How this domain, whatever the domain you selected, is not representing that, right?
Yeah, that water is coming and it's flowing through the city. That map we have, and it is overflowing. That will show it. That is there. But I think there is one notion still. Many people think that in 2015, the flood took place because of huge release from Chembalbakum Lake, but that's not completely true. Because if we open the full gate also, there is maximum release. Even if we force that, we will not get that type of inundation. Actually, so much of rain was there, and from Kanchipuram and all other sides, all water came and it went to the Adyar River. And it is far beyond its carrying capacity. So that's why huge flood was there.
The domain size for hydraulic model.
I think it will be around how much? 12 kilometers length from the coast. Saidapet bridge is there. This bridge is there. Nandanbakam or something, that bridge. Miyat Hospital, you remember? Yeah, after that. Okay, so maybe you can.
Good afternoon, everyone. I will first discuss about some of my results from 2023 mission flood simulation, and then I will go for a demo of hydrological modeling. So these are some results from initial hydrological modeling with the raw radar data, which I was not blended initially with rain gauges. Then the black one shows the observed flow from Chembalbakum reservoir, and Chembalbakum reservoir is the only one where we have the measured flow. So in the downstream of the river basin, we don't have any stream gauges. So we are calibrating our model with respect to Chembalbakum reservoir flow. So when we compare the results with radar data, we are getting very low estimate. And when we compare with the rain gauge data also, we can see the radar data is following the temporal variation, but it's not up to the mark of rain gauges. And so from the hydraulic model also, we found that we have to improvise the quantitative precipitation. So we are using radar rain gauge data blending techniques.
So when you say, so it follows temporal variability, but it doesn't match the value. Is it higher or lower? I cannot, there's so many curves I cannot see.
Yeah, it's lower.
Radar is lower.
Yeah, radar is lower. Okay. Radar is the lower.
Oh, thanks.
And we followed two methods. We have first approached a random forest model, then we have followed a linear regression model. Then we found out which one is performing better in between this one. So for gauges and correlates as radar precipitation at the exact pixel of the rain gauge location. Then the location variables such as latitude, longitude of the radar, the rain gauges, then the elevation, then the distance from the coast to that particular rain gauge station.
Okay. Yeah. I don't want to scare you by asking too many questions. So to get radar rainfall, this is the expand radar.
Expand radar.
And did you use this? Is there an equation?
No, this is from KDP.
I use KDP. Okay. They gave you the KDP. I gave you the KDP. Oh my goodness. But I cannot ask more questions.
This is exactly the point I was mentioning in the morning. So what to do if it is underestimating? I don't know. There is one value higher, one value lower. I don't know it is underestimating.
No, it's okay. Just keep going. We'll get there.
So this is the result we got from linear model and this is from random forest model, and we check how the variables are correlates are sensitive to our model. So we found distance from coastal is very less sensitive and elevation and latitude variables are highly sensitive to the models. This is a spatial variability plot for different models. And this is the blended products for different models. I have, I think it's not visible properly. I have marked the rain gauges here with the same color pattern. And with this data, we are going for hydrological modeling. And this is the overall methodology of hydrologic modeling. Earlier, Sir has explained different processes in hydrological modeling. So our basic input will be in meteorological model rain gauge data. We are using radar rainfall and rain gauge data for meteorological model. In our model, we can also include different meteorological parameters such as temperature, evaporation, etc. But as of now, since it is an event-based, we are simulating an event, so we are only considering meteorological parameters, rainfall only. So then our input will be the digital elevation model, and from land, and the other one is land use, land cover, and soil. From land cover and soil, we estimate curve number. Curve number will explain you how the combination of soil and land use cover is about to produce how much potential to produce runoff. So that combination of this product will give you curve number. Then this model will go to basin model. I'll demonstrate how will we create a basin model. Then we will run the simulation. From the runoff, we will with the observed data, we will calculate the model. Then further, we will go for hydraulic modeling. So these are the inputs: digital elevation model, soil data, and land use, land cover. So from soil and land use, we will arrive at curve number. After running the hydrological model, we will get different basins, sub-basins. So from each sub-basin, the hydrological model finally will give how much cumulative precipitation is happened for each event. So I have plotted the cumulative precipitation at sub-basin scale after the Mishok cyclonic storm event. So each data shows different distribution at sub-basin scale. If we compare rain gauge and the radar data, it is showing large variation, but somehow we are able to capture the variation of radar and rain gauge in both the radar forest model and radar linear regression model. So sir initially have explained how the discharge, what we are getting from hydrological modeling is the discharge. So this is the discharge we got from this is the discharge data we got from the hydrological model. The first one is the discharge at inflow at Chandramukha reservoir, and this one is the discharge at the sink. That's the outlet of this total basin. So we don't have, as I explained, we don't have any discharge measure in the downstream. We have calibrated at the upstream. So when we see the rain gauge data, our model is calibrated with rain gauge data only. So we check when we check the rain gauge data, it is showing high variability with respect to observed one. But our model, random forest model and linear model, is about to capture the peak and the flow pattern of the observed data. And here I have mentioned the time to peak in each model. So rain gauge data is showing, rain gauge data is predicting that this flow, this peak discharge is occurring before the actual peak discharge. But radar is almost capturing the discharge, but then also it's having some delay.
What is the delay? Trying to keep up with your graph. What's the difference in delay between gauge and the radar?
Gauge and the radar.
Peak delay.
Oh, peak delay. Raw radar data.
You said the gauge is very different from the peak.
The gauge is different from Chandramukha reservoirs.
I'll ask you later.
And we also got good result when we compared with the calibration. So for random forest model, we almost got an R-square value of 0.937. Whereas multilinear regression model got higher value of 0.946. But when we compare the raw data in NSE scale, it's showing minus value. So we can't take it as for further simulation with radar data. So after that, we have gone for a distributed hydraulic model, full 2D hydraulic model. We considered entire Chennai basin as domain. As Sarah explained earlier, before we will, what we are doing is we will take the discharge from Chandramukha reservoir, and then we will route that to the downstream of the sub-basin, downstream of the basin. But for this model, since we have high resolution radar data, we have gone for a full 2D hydraulic model for the entire basin. These are the pattern of inundation map we have got from different models. This one is rain gauge models and linear model and random forest model. This is also showing good performance with the observed depth values. Next, I will go for a just demonstration of how we are setting hydrologic model of the Chennai river base, Adyar river basin. Yeah.
So, can you still tell me? She said the gauge data, if you use the model, it didn't get the peak timing right.
Yes.
But data got it better, but it's still not good. That's what I heard. But how much? I couldn't figure out from your slides. Can you go back to your slide? Yeah, you said observe 630.
Yeah. Observe 630 and rain gauge is at December 4th, 8 p.m.
Like a 1 day delay.
10 hours.
There is a what delay?
Yes.
Radar delay is how much?
Almost delay more than 14 minutes. Raw data, but the model which we have prepared is delays about 250, 2 hours.
3 hour delay?
Yeah, almost 3.
Everything is delayed. Nobody is predicting ahead.
Yeah.
Okay.
That's what I said. Even though after getting the performance matrix good, we are not able to predict exact peak discharge time.
So what's the RKDP did you use equation?
That equation which is given in textbook, K into KDP divided by F always to
Everything you're blaming me.
No.
I think that's.
So the reason I'm asking is, I actually recalibrated the KDP for one event using disjointed data and,
2020.
sorry?
I think sir had told that it is for 2021.
What is this for?
This is 2023.
23?
Yeah.
That's fine. I'm not worried about 21 versus 23. It's just like, I've never seen, our KDP across before, Chennai. So I wanted to compare against that equation sometime. I'll talk to you offline. I didn't know you would see that spot.
Can you, sorry, can you go back to rainfall estimation from radar machine? No, back there was a slide with 6, the previous one. Yes, yes. And did you compare, make a comparison between rain gauge and weather radar estimation among the time?
Yes, sir.
What have you seen?
This is the actual comparison we have made. This one is with the actual radar data without processing with rain gauges. So it's showing no estimation. I have one more plot. Yeah, this one is the blue one is with the rain gauges and the yellow one is with the actual radar data.
So in some cases, if I don't miss at the beginning, there is no rain from radar.
No.
Yeah, that's.
Actually, this I don't know why it's showing so, but it's not showing any raining radar data for that.
Yeah.
No, I think I'll go back to the slide. So what I could understand with her discussion with her, what is happening, this radar is also not covering the entire basin. So that is also another limitation. So one is coverage is not there, and then we have some other issues. So we can't blame directly the radar measurement. Maybe nearby area we should check, but then we don't have rain gauge there. So we are limited by that, all these things.
Yeah, we have almost 5 rain gauges situated near to the radar location, and rest of the 4 rain gauges are situated short.
Okay, what is the resolution of your radios? The gauge and the radar? The rain rate, what you plotted on the time series?
This I plotted as in hours, because rain gauge data is in hourly.
MM per hour.
No, rain gauge, rain gauge data we have 1 hour. Any other questions?
So, except that this resolution, what is the difference between small land surface model and this one? Small land surface model. No land surface model.
Land surface model.
What's the difference between except resolution? What's the difference? Small.
Is asking what is the difference between this model and OA land surface model.
I think sir can explain better than me.
That other model, that is also a hydrological model?
Yeah.
Yeah, I think maybe the resolution scale. This model, what we are using HMS, it's quite detailed when the water set size is relatively small. If we go for very large scale water set, then we have to simplify the hydrological processes also. Yeah. So then infiltration, evapotranspiration, many things will be again simplified.
Any other question?
Okay, so we can move forward. So I have prepared a PPT like how detailed steps we have involved in the hydrological modeling. Since we have time constraints, so I'm not going that much detail, but I will explain how we are going through the procedure in HMS model. So first one is we have to set up the terrain model of how HMS model. Then we have to set up the basin model, then meteorological model, then computation run, then we will analyze the results. In terrain model, what will be for the input will be the digital elevation model. Here for Chennai basin, we have we got a LIDAR DM of 2 meter resolution. So since it is computationally higher in HMS, so it's not it's taking more time for deriving the drainage network. We have resolved that into 30-meter resolution, and we have identified the sub-basin, and further modeling be done on that DM. So I have mentioned other source of freely available digital elevation model also. And regarding HMS model we can do in semi-distributed and in lumped manner. It's freely available software. You can directly go to HMS. You can type HMS download. You can directly it will directly redirect you into the site, and you can download the version whichever operating system you have.
HMS, we have only 7 gauges. How can you run it distributed?
Yes, if we are choosing the rain gauge method for meteorological model, we will select the method how it will go. It will be interpolated over the basin. So if we are selecting the rain gauges, we have multiple methods like interpolation in this and collision method.
Or something. 7 gauges you use. Yeah. It's a speed of data. I mean.
So this is how the HMS interface will look like. So first we have to create a new model. For those who want to try the model, I have shared the data set which we have incorporated.
I don't think too many hydrological people are here. So let us not go to the software and give the demo.
Okay.
Through PPT, you explain it. Those who will be interested later on maybe can explore, and that time we can we can be in touch with us. Yeah. Yeah. So now you can explain it the overall process.
Okay, first we will import the digital elevation model into the terrain model. So which will be from which only we will derive the drainage network and sub-basins. So these are the steps. I have given a screenshot also. If you want, you can refer that. So next one is the basin model. Basin model, the concept of basin model is to translate hydrology and in manageable sections. Your structured representation of the stream system. So I have given the steps how to create. We have to
Yeah. So what I will do is, okay, you just fill the gaps in between. So even if you run any other hydrological model, what model based on slope and other factors, it will go for subbasin creation. We don't define it. It is GIS based system. In the background, it will do small basin. Somewhere like a river. That's what she will explain. Yeah.
Later or after creating a basin model, this is assigning projection, which is a step. We will assign the projection of our basin model. So, which means simply assigning the coordinate system. And
yeah, and here again, like you see that this model is from USA. They still follow that British system, right? Those units, US Army Corps of Engineers, they still follow that British units. But we don't follow, so we go for SI unit. So projection and other things we have to set here.
so the next step is, main step is watershed delineation, through which only we will arrive the sub-basin and stream network of our basin. So the involved steps in this one is pre-processing pre-processing drainages and identifying streams. In pre-processing sinks, we will mainly doing is a pit, applying a pit removal algorithm. And we will input that raster, and which will be and after there will be hydrologically corrected. Even if it is not corrected hydrologically, we have that option also. The line reconditioning option will correct your dam into hydrologically correctable. And after that, we will go for pre-processing sink. So basically, filling the pits. And the next one is pre-processing drainages, which will identify the flow direction and flow accumulation of each grade cell axis. For each cell, it will identify which is the flow direction of the digital elevation model and how it's the and how the flow accumulation is happening. And next one is the identifying streams, in which we will apply the threshold. So how much intensively we have to calculate the drainages, in which we have to assign some values. In this one, this one is in SI system. We have to give it in kilometer square. If it is in US customary student, it will be in mile square. So here we will specify in how much intensively we wanted the computation. If you go for smaller value, it will create smaller sub-basin. But if you don't want that much finer resolution scale, you can give higher value. So based on that value will be your subbasin will be created.
So again, this subbasin, how many numbers? It depends on what type of data available is there. If you have very limited data, then there is no point in going for very small surface. DEM, one is like open source data is the SRTM.
Oh, it's still from SRTM.
No, but we are Chennai, fortunately, it is a little old, but we have high resolution data accessibility. It was laggard data. Yeah, so now what we are doing, we do blending because that data is becoming old, 2010 data. And now we have got a 2.5 meter resolution carto set.
Oh.
So we have. That carto set is from here. ISRO, I think, right? Yeah. So they have 2.5 meter. But again, the vertical accuracy is still an issue.
Next one, we have to import the breakpoint. Breakpoint which means the sink or outlet of the total subbasin. Based on that, will our that only our basin got delineated. So we have to specify for our river where is the outlet. So you can import that in like sometimes you won't be able to identify the outlet point of your river. In that case, you can georeference that from either QGIS or Google Earth or something, and you can import directly that into a model, or you can identify the streams and identify the breakpoint in the HMS interface itself. Then you can import that. Based on that, it will get the basin will get delineated.
Yeah. So what does it mean in basin? Water state means there is only one outlet. Right. So if there is rain, then all water will go to that point. Now, in this case, we have a river outlet is there. So it should merge automatically there. Now, all the pre-processing we are doing in the QGIS almost in an automatic way, it may not match. Right. Yeah. So that should not be the case. So that's what it is telling. Since we know where is the outlet, in QGIS or any other GIS software beforehand, you mark it and then you force it. So then your delineation means demarcation. Demarcation of the watershed will be created.
But I'm just curious. How far apart? Okay. How far apart is that model-based outlet?
Did you try that thing without forcing?
Yeah.
How much will be the difference?
Difference, it's not coming that much difference. Almost same.
Yeah, because if you have good quality DEM, that will be great.
There is not that much. How much? How much is that much?
Sir, for delineating, we will import the breakpoint. If we are not much variation come into discharge, but you will get some difference in the subbasin area. Area-wise, it will have some difference. Sometimes, if you import breakpoint at some point near to the sea, so you will get multiple basin at the downstreams. That also will happen. So
I understand all that. Okay.
Yeah.
What happened?
Oh, like quantitatively, I haven't compared it. How much is coming?
So if it is in bathymetry technique they have done, it is like 2 meters. Like in Mumbai, they have the 2 meters.
If you have this is the key thing, this bathymetry. When bathymetry means in the reverse side, otherwise, this digital elevation model plays significant role.
Next one, we are going to setting up the parameters, that is for representing each of the processes in hydrological cycle. We will represent that through different mathematical equations or models. So we have different parameters which represents each models. First one, for accounting the losses, as I has explained earlier, what are the losses and all. So for representing the losses, we are using SES curve number method, which is invented by US Department of Agriculture in 1954. And it's most commonly used for urban watersheds, and found out more applicable since less parameter are dealt with this model. So we are going to use SES curve number method. Curve number means it's a dimensionless number which have been plotted by doing different analysis in different watershed, and they have plotted the precipitation and excess precipitation, which means the precipitation part which is going to run off, and we have and they have plotted some curves, and they have given some number for the curves. Through that, they have derived this curve number. So curve number will ranges from 0 to 100. If your area is impervious and if it is water, we will take a higher curve number. For example, if you are taking water, you will assign that water to curve number 100. And if it is vegetation or something which will produce less runoff, you will give a lesser value, around 36, 35. Based on NLCD report 2019, you can give 36, 39 extra. And another thing is hydrological soil group. Sorry. And another thing is hydrological soil group, which is the classification based on the runoff potential of each soil group. Based on that, they have classified the soil group into ABCD 4 classes. Each will having the runoff potential ranges. Based on that only, we will assign the curve number. And these are some basic equation which we are dealing with. SES curve number is basically is based on the water balance equation, and these are just a formula how they are arriving, and their what are their assumptions and all, and the equations. Yeah, I'm not going detail to it. And next one is setting the transform parameter, which is transform means we have to convert the excess precipitation into runoff form. So how will we taking the runoff into the excess precipitation to runoff? So these are the equation we have used for transforming the excess precipitation into runoff. This method is called SES unit hydrograph method, and I have given the parameters also here. The parameters considered in this method is time lag and time of conservation. The advantages of SES unit hydrograph method is it's only using one parameter, that is time lag. And next one, for representing the base flow, we will use the method precision. And for routing methods, as sir has explained, the different routing methods, we have different routing methods: kinematic wave method, dynamic wave method, Muskingum method, Muskingum French method, and different methods are there. We are using Muskingum method, and based on that, we are giving some parameters. It will be too much clear into. So then discretization we have to specify. Since we are giving a gridded rainfall, we have to specify in which mode of discretization it's happening. So we will specify a grid of whatever size which you want. So we will force that into the subbasin, and based on that, this the subbasin will gridded into your resolution. So next one is importing the meteorological parameter. We can import different meteorological parameter, but as of now, we are only incorporating the rainfall data. This is the rainfall data, radar rainfall data clipped with our study area. So in HMS model, we have to give every raster in time series manner. For that, we have a utility program called ASCII to DSS, which is an executable program. You can write simple text file, then you can text file as batch file, then you can run it, then it will store each raster file information in time series format. That's how we are importing the radar data into the model. So for each raster data, we will assign the time, coordinate system, and the resolution, everything. So it will directly take into DSS format. Or another method you can use is, if you are going for rain gauge method, you can import the rain gauge data as point rainfall data. Then you can interpolate within your basin based on some methods called these are polygon methods, or you can use some method called specific hydrograph, anything. Or otherwise, you can create the rain gauges data, and that data also you can import as a raster form into hydrological model.
So it's like that. Yes.
Yeah.
Right. So the first paragraph, the temperature, and precipitation, pressure, and wind speed.
Yeah.
At the base level.
Yeah. So whatever the gauges are, we can import that into point information itself. Or if you have,
I think let us limit it to the radar. That will be good. So what C is telling, it's like a stat matrix. Time T1, entire area, what is the radar measured rainfall data? That is like one map, raster map. Then time T2, another map. T3, another map. So in this way, we are taking the radar data. And that will be as a batch file, and it will go as input.
How much area of the map is actually covered by radar and not covered by radar?
Actually, we have only one radar. The remaining part we are blending.
How much area?
no, so actually the radar is covering entire area. So, but in the
Wait.
actually the thing is, we got good observation at the downstream, but when we go to the upstream, we are not matching the radar and rain gauge data, not at all. So that's why we go for blending technique, and in the downstream also we are not able to match the rain gauge data and radar data, but it is following the temporal variation in rain gauges. That's why we go for blending. It's covering it within the radar range. The entire basin is covering within the radar range. But when we consider entire Chennai basin, if you are going for modeling entire Chennai basin, it's not covering exactly within the radar range.
How many rain gauges blended? 7, right?
9.
Why don't you go for a IMAX? Whatever.
Yeah.
You can use that. You will have a good mapping.
IMAG also we have tried that. So we have also tried with IMAG also, but radar is showing better result than IMAG. Radar is showing very poor. Huh?
Let's also radar data from this base.
No, I am telling about topographical radar. Actually, IMAG data is performing very less than rain gauges and topographical radar, but we haven't checked.
So I think each product is different. Yeah, so and our only cost is rain gauge. We know the limitation. We cannot say that is the benchmark. But at least whatever measurement data is there, flow and other thing, from there we are going back that something is happening there.
I have one question here.
Yeah.
You are reading the radar.
So you are building the radar data, right? At what height? So what height are you, inputting it to the model?
What height means?
So what height are you taking? So since you're building the radar data, you are not using the polar data.
I think this data is a 2 degree elevation.
Okay, but you have mentioned there it was graded in the previous slide, I think. Okay.
If you want grading further, you can grade that also in DSS file. That's what I.
But it's 2 degree elevation.
Yeah, 2 degree. This is simply how we are specifying the path. After importing the data also, we have to specify how the naming convention, how the start time and end time is taken from the raster file. We have to specify that. That's a simple step I have mentioned here. The next one is we have to specify the end time and start time of our simulation. From which date to which date we have to run our model. That step we will specify here. And in how much time step our model want to run, that also we are going to specify here. We have radar data at 10 minutes interval, so our model is going for running at 10 minutes time interval. And this model have run for from 3rd December to 7th December. Our model has run for only 4 days. It's computation steps only. And this is the results we have got from there's a provision of incorporating the observed flow in the model itself. So we can incorporate the reservoir discharge in the model itself. So the model itself do that primarily show how much variation is happening, and it will show how much calibration results initially. So based on that only we will go for further optimization and calibration. So after calibration, the results are shown here for the blended model. So black one is the observed flow and the blue one is the data with radar engaged blended one at chamber reservoir. So this kind of data, like discharge data, you can get at each subbasin scale basis, and accumulated precipitation at each time series you can get in subbasin scale basis, base flow, evapor transpiration, everything you will get in subbasin scale basis. So you can analyze which subbasin having much contribution to your hydrologic model and how much it's contributing to a total discharge from the total subbasin. Yeah, that's it.
Yeah, so regarding hydrological model, again, this is event-based model, like one event. If you want to run multiple events, then we call it continuous means model. So that is another type of model. And this is in quite high resolution. And we have still limited data for Chennai. Now we are in touch with this brother and Chandrasekhar. So I think it's a good time for us and good opportunity so that we can go for engineering application. That's what I would say. Means how to utilize this product. Maybe we need to go for some kind of calibration, correction, or whatever we say. We'll make it usable for hydraulic purpose. And then we can go for engineering solution. That is the whole purpose. With that, we have started. Maybe we'll try Mumbai when we have better radar data and engaged data. In Chennai, it is still limited. Maybe after 2 years, we are getting more radars. That time, I think things will be set for Chennai. So if you have any other questions, you can ask. Otherwise, we will wind up.
maybe set 4 or 5 super gauge locations in Mumbai in the radar domain, where you put 2 rain gauges and the decilometer in the same place, or something like that.
Yeah, we have. So we have like 4 sites where we have rain gauges and decilometer.
How many rain gauges?
Rain gauges means like it is like 1 rain gauges only at
You
one.
need to put more than one.
At this time, we are putting the 2 rain gauges at the 4 super sites. With 1 decilometer will be there. And that is actually also site.
Council is not here, I will only ask.
Yeah, right now we have the impact decilometer, but we will be going
When he is not there, go buy something else. He doesn't want to get out of that yours system. I pass you on.
Yeah, the fall velocity will be there, that's the advantage of that one. So yeah, we will.
I will send you. I'm not joking.
Yeah, so then, like,
I haven't.
higher, so maybe that's why it is not capturing, I don't know. That's why it's,
Yeah, I'll show the location. Because that's a clipped one, it's not covering in the data.
Still, isn't the elevation higher?
Yeah, but in city, you have to live with that one. You cannot get ideally 0 degree. Up to 3 degree, if you are getting, that's the concept and that's put like in the Kasan equal. So you have to do the close variant.
What is the range extension?
Yes, that's right.
Yeah.
No, the radar graded one. That spatial map you have shown, right?
Art special.
This map can you show?
Yeah. Next one with a graded thing you have shown, right?
Graded one, for.
Here also you can see. Where is the radar?
This is a radar.
Radar location.
Yeah.
That is a point one, I think.
Yeah. Red one.
Oh.
The distance with the western part.
I don't know, so.
This one is a radar.
Sorry.
Oh, that's the radar.
Yeah, and the distance with the western border. How long is, how much is the distance from the radar to the western part of the basin?
That's the scale, whole picture.
Whole picture, the total base.
Kilometers. I think it will be 25. Yeah, from that point to the furthest point.
Yes,
More than that.
more than that.
30 kilometers.
25.
No, more than that. 30.
Almost for 30, 39.
I think maybe.
I need your help. There is another radar in the sea helicopter.
Yeah.
That's right. If by chance that can capture something, we can try that.
Yeah, we can.
There is
So we don't have access to that data.
There is one in Kalpa.
Calcutta.
That's what it is. We are.
Then Calcutta.
Kalpakam was not installed by 2021, right? 23. But it was functioning. Remind me. I will catch that.
Yeah, I think that we can improve.
Yeah. I don't know. Functioning, right? Yeah, actually, that's right. Alpacam is a better choice. How far is Alpacam? How far is Alpacam? It's definitely closer than sea.
No, but again, here what is happening, too many buildings, high rise.
No, no, I know. That's the
That side is only little bit here.
Any other questions? Let's thank Dr. Curie and Arita.
60 kilometers.
2019, right? Yeah.
Now I invite Mr. Chandrasekhar for some announcements. Let's take a moment to felicitate the 3 lead speakers for today. I invite Professor Chandra to honor Dr. Luca. Dr. Luca Valini, everyone. I now invite Dr. Panditira to felicitate the next speaker. Sir, can you please wait? I request Dr. Panditira to kindly felicitate Dr. Renzo Becchini. Can you have a big round of applause, everyone? Now I request Professor Chandrasekhar to kindly felicitate Professor Professor Samindra Curie. I'm so sorry. Professor Samindra Curie.
He sent his student. Yeah.
Yeah, so actually, I think this is for all those who are aspiring to faculties for scientists. We need to keep our eyes open. So suddenly, one day I got a call from IIT Kharagpur, Professor Chandra, and he started talking in Bengali. And he said, I am in Kharagpur. Then I told, who is this guy? I don't know. Then he told, no, I am with a DJ. DJ is my supervisor.
It's supervisor.
PhD supervisor.
He went to school at around the same time.
And there's same batch, Dhruva Jyoti. And then he came to Chennai. Then he was telling, we are we're working on radar, rainfall, this, that. And we are looking for someone who can do hydrology, hydraulic simulation. And from that, then I told, no, I have got a very good student this semester.
And she is also interested, let us try. So then initially, Anita started, and then in summer, he was kind to give a special scholarship for 3 months to Anita. And she was there, she picked up. And now again, he suggested something for Anita for 2 weeks. Maybe again, if she can stay there for some time, clean it up, and come up with better results, then again we'll continue. And now we have more known people here, more data set, more problems, more solutions. I think it will be a nice time then. Thank you.
It's my time to embarrass Sarika now. So, tell you a funny thing. Oh, before that. Funny story. What? I don't even have passport. I don't have anything. So it's not possible. Then Somendra said, what nonsense are you talking? I'll get you passport in one day. You remember that? So, but for Somendra's pushing, she might not have come.
I would like to request Dr. Luca Baldini to the stage and felicitate our youngest speaker, B.V. Arita. Big round of applause. Here, everyone. Now for the announcements.
Okay. So this is what is called as party crashing. They don't know. I just said, I want to actually take a moment to thank not only Pandit Rai, also Subrata Das and his colleagues. And I will really tell you, I gave them a lot of hard time for this class. He said, then I said, I will come only in December. And we cannot do it in December. Okay, I will come only in February. They are not letting us do it in February. Then I said, I won't come. But I have said no to him so many times, but he is very calm. Also, oh, don't worry. I've given really a hard time. But and then I have to, every time he changes something, I have to keep changing these people. But one time, no, Luca is a very busy guy. And though he looks very simple here, he's on so many international commissions and he's on the review committee for healthcare, this, that, this, and he's like traveling to Japan here, there. And these two guys are also very busy. And they're preparing for the next Winter Olympics and then redoing all that. So I had that side of it, but he had to deal with me. Anything he asked, I would say, no, I cannot come. They will come and talk. I will do only remotely. He was very patient. So let's give Subrata a big hand. It's like, maybe after you, I'm sure you could have help from your team. You can tell them also.
Yeah.
And,
Sachin is there.
yeah, I was looking at Sachin. Get.
Arshad, Hari.
Very, very see.
They are here.
Oh, yeah.
Yes. Yeah. Students.
So, but from my side, I gave him a really hard time, but finally everything came together.
Yeah.
And thank you.
Thank you.
I just wanted to thank you personally, and that's why I inserted myself into an announcement. Now, what is understanding between them and the team? So can I declare tea break? She has given permission, and let's declare tea break.
Please assemble back at 4:30.
Thank you. I invite Dr. Renzo Becchini for the recitation.
So, good afternoon, everybody. So we have arranged some mix of slides for the afternoon with some problems, some discussion, and some hands-on exercise with DSD analysis. So here we have a couple of problems from our book. So my suggestion is I can leave this slide on after the session that we can briefly see now these problems, then you can think about it, and maybe tomorrow in the afternoon session we can discuss the solution. These are actually quite simple problems, but are very useful to get the hint of the, with the real numbers about the rainfall, reflectivity, and the volumes and of the radar, and I think it's very interesting. So if you could think about this, maybe between today and tomorrow, then tomorrow afternoon we can get back this. And so I would only get back from this morning with a few slides about because we've been talking about columns of differential reflectivity. We had some discussion also with some of you, and I just want to show some slides. Also, Subrata is not here because we were discussing about the dynamics of the CDR for C-band. So I have some slides that can be interesting. So CDR columns you see in this diagram is when you have a strong updraft that is able to carry a lot of liquid drops that becomes super drops as they go farther away above the melting layer. And then this creates a specific signature of CDR, which distinguishes from the rest of the environment where frozen particles are dominating. And the importance of this is that there are several studies to show that this feature has a prognostic value, so they can be used to see in advance how the thunderstorm will develop. So this is an example from our C-band radar in Italy. This is a PPI at 5.8 degree, 4.4 degree elevation reflectivity and CDR. And you can see I marked here with this black line the limit, the freezing level, this relatively high elevation PPI. You can see positive values near the radar, which means below the melting layer. And then, so farther away from this line, it should be above the melting layer in the ice region. But you see that there are spots of very high CDR. And actually, this you can see also some differential attenuation beyond these spots. So it actually means that there are liquid drops of late that give this high CDR value and actually differential attenuation after that. If we take vertical sections of this, you see the reflectivity. There is a main cell here with values up to 60 dBc near the ground, and there is another cell actually ahead of the storm. This is like a child cell that is developing, so it's less intense but developing higher, and you see this CDR column. You see actually CDR values up to 7 dB here, which are really likely to come from melting hail, which produce very oblate particles, actually more oblate than pure raindrops, because the effect of having a solid nucleus allows the particle to reach larger dimension and a higher degree of oblateness before breaking out. And you can see this column of CDR, which extend like a couple of kilometers above the melting level. Then I have a sequence, sorry, the scale is different here, but this is a vertical cut through a volume scan. So we have a volume of 11 elevations. So just extracted this cut in a specific direction, in the direction of the storm propagation, to see how this feature evolved over time. So we see at 6:35 p.m. there was a first signature of this column, of this CDR value above the freezing level. Then 5 minutes later, you can see this feature is more marked. We have CDR in excess of 3 dB, quite consistently across 3 elevations. And you see that reflectivity has not reached yet a very extremely high value. And then we see at 6:45, the CDR column already extinguishing, but now the reflectivity attaining very large value aloft. In this case, above 55 and 60 dBc. Next, the CDR column is completely gone, but the reflectivity keeps increasing aloft and then propagates with a larger value towards the ground. So the highest values of reflectivity aloft are detected 15 minutes after the maximum of the CDR column. And then the maximum mid-level at the 50 dB here, and then the maximum value at the ground, in this case above 60 dBc, were detected like about 20 minutes, 25 minutes after the CDR column. So this is an example. There are several studies that analyze a large number of events, which actually concluded that these CDR signatures are very useful for prognostic application and can provide a useful lead time to predict the intensification of convective storms. So this was one thing that was like hanging from tomorrow. And another thing that I didn't have the time to discuss this morning was these bright band signatures in dual polarization parameters. So we know the bright band we're used to see in the reflectivity. There is this enhancement due to the melting snow, and but we had specific signatures in all the variables, particular reflectivity, differential reflectivity, and the correlation coefficients. So from the physical point of view, what is this melting layer signature due to? I mean, above the melting layer, from the microphysical point of view, we have aggregations, and then when we approach the freezing level, the electric constant increases, goes from the electric constant of ice, and gradually we get the electric constant of water, which is 5 times larger. K square is 0.93 about for almost all the frequency for water, and 0.17, around 0.17 for ice. So this increase in the electric constant causes an increase of reflectivity. Then there is an increase in density because, of course, melting particle becomes more dense. An increase in the terminal in the particles fall speed, which decrease the number concentration, and this gives rise to the diminishing of reflectivity in the lower part of the melting layer, and finally break up because these large particles, partially frozen, will start to break up when they are completely melting. So all this causes the particular signatures that we have seen in the slide before, and is summarized in these vertical profiles. So we have this is an average from a scan at 15 degree elevation, and we see the nose in reflectivity. We see another nose very similar in CDR, and a minimum reverse knows in the correlation coefficient, which is due to the mixing of different particles. You see there are slight differences in the height of this peak, and typically the peak in CDR is observed at a lower altitude with respect to reflectivity, and ρHV is typically somewhere in the middle. This is due to the fact that when snow particles melt, they start to melt from the tips of the snowflakes. So the first effect seen by the radar is the increase in the dielectric constant, while the shape of the snowflakes do not change too much. So it's still spherical, but it starts to backscatter more due to a change in the dielectric constant. So this is the reason why reflectivity starts to increase before CDR, which is reflecting the shape. So as soon as melting progresses, I mean, the snowflakes start to, also the internal parts start to melt, start to become oblate, and then also CDR is increasing. That's the main reason. And here we have a vertical pointing scan, and this is a Doppler spectrum where you see this was collected right before this one. So we did a scan at 90-degree elevation, collected the Doppler spectrum, and then we did this to observe both the dual polarization parameter and the vertical velocity. And you see here the vertical velocity, the spectrum is centered on values of between -1 or -2 meters per second, which is the typical fall velocity of snow particles. Then we have a phase here where the spectrum becomes bimodal. We still have one peak around -2 meters per second, but there is a second peak that is appearing here. And then when particles start to completely melt, we have the typical spectrum of rainfall, with a peak around -7 meters per second. And this is an idea. You see, it's very close to the minimum of ρHV of the presence of a mixture of ice particle. The larger particles are still in mainly in the ice phase, while smaller particles, which melt faster, have already probably are transitioning to the liquid phase. So then, okay, to summarize, this morning talk about microphysical processes. I wanted to discuss with you this synthesis. I made these plots that summarize the main warm rain processes that we've been talking about this morning. And I would like to ask you, to which process can we assign these images here? We discussed coalescence, breakup, evaporation, and size sorting. So we can start from the left if you want.
Evaporation.
Evaporation. Then, I mean, it's good. I don't remember exactly. I have to check the next one. I think it's reasonable. Evaporation, decreasing reflectivity, and CDR likely increasing. Then what this causing a decrease of reflectivity and an increase of CDR. And maybe this is easier, increase of both, increase towards the ground, which is a process that may lead to an increase of reflectivity as we move towards the ground, and at the same time increase CDR. So it's something that, yes, this is collision coalescence, of course, and this is something like the reverse. So what would this be? Breakup, and this, okay, the only left is the size sorting. So this was, yes, okay, it's correct. So that was to summarize what we've seen this morning. And this, of course, this is qualitative. This is very useful for visual interpretation and to go a little bit beyond the interpretation of local information, but looking at the whole picture whenever possible. This dual polarization observation tell us a lot when about processes when you look in space and in time, the evolution of the parameters. Okay, this is another exercise I would like to discuss with you. So I have this radar RHI from the Chile radar in Colorado, and we have reflectivity, CDR, ROHV, and KDP. So based on this information, what we discussed, what can we tell about the possible dominant hydrometer partitioning of this space? Is it something that you clearly see and make you tell that I mean, we have rain in this place, we have snow, we may have hail or something else? What would you guess? I mean, here we have a core of very strong reflectivity, and I marked the 60 EBC contour here for reference in all the panels. And here we have this ROHV, this signature is also very typical.
Hailstorm and
Yes, this is a hailstorm. CDR very low with the high reflectivity, but we also have a very high value of KDP. So what this KDP tell us here respect to the information provided by ZH and CDR? Sorry? Melting hail and probably yes, and probably also a lot of rain. Yes, very often hail does not come alone, but also with hail. And then here we have a more stratiform region. You can see that there is a stratification here. You can see very well in CDR and in ROHV. So actually, this is also something very common that we don't have. I mean, only convection or only stratiform. Many instances in the same PPI or RHI, you can see convective region, stratiform region, and like in this case, if we see this,
Can you go back to the previous one? Just wondering what happened to that OHV there after that.
Yeah. Yes, I think this is degraded probably due to low signals.
S-band.
Yes, S-band, but it's very, yes, I don't have the signal to noise ratio, so that would be useful to interpret this. But I guess it's mainly due to the quality of the signal that
You have a very good CDR.
Yeah, good ZDR and reflectivity, but OHV suddenly drops to.
yes. Sorry.
Best.
I know PDP also became more noisy here in the last part.
Yeah, but
And Roche, but yes, as you say, ZDR still looks good.
Yeah, ZDR is good, but your OHV suddenly drop. It's very interesting to see this time. What is the value of OHV?
Here it drops to 90. The yellow is
0.93,
92, 93. And yes, I'm not aware. Yeah, it is also very low level, so I'm not aware of any clutter that may be affecting the measurements here. And so.
And so there are some columns of depleted OHV between 25.
This.
Below the
This.
Those are the columns of very low OHV.
But I think that these are just in the very low signal to noise.
But that is within the range set.
But these, you mean this? Yeah. Yes, but these are, yes, in the range set, but where you have a relatively weak signal. So this ROHV probably was not corrected for noise. Because normally from the radar, I mean, from the signal processor, you get the ROHV, often it is not correct.
You have a strong ZDR, reflectivity is low, but ZDR is high.
Yes, this may mark the presence of large drops. Yes, and the ROHV can be, can be due to mixing maybe of large drops and very extreme DSD, but also in part due to the low signal to noise. Because actually, yes, the correlation coefficient is highly affected by the signal to noise, and you should correct this formula based on actually the noise and CBR to correct OHV. And probably in this case, it was not done, as you see also on the top, where the signal becomes low, OHV tends to degrade. So this is the output of one automatic hydrometer classification partitioning, which shows in blue the melting layer, basically wet ice. This purple would be proper. We've been talking before in the tea break, and yellow is hail, and the orange is rain, hail mixed with hail. And this partitioning is made possible thanks to ADP. Because ADP is sensitive to rain, but it's insensitive to hail. So if we only had C and CDR, it would have been more difficult to identify this as a heavy rainfall region respect to only hail. And then, of course, we have rain. So with that, I think that we can try our DSD analysis exercise. So we have shared R code, source code, and I don't know if any of you is use R general. You all use MATLAB? Oh. MATLAB. MATLAB and Python. We started to use R a long time ago, maybe because it's free, and actually it became very popular and very powerful. In general, we can do everything that we can do with MATLAB, we can do it with R, but for free. So that's why we use it a lot. So, they have installed R on these computers, and I don't know if I have shared the code. I can also run it from this, and
the code is shared with you all. You just check your name on 44. His name is there, and everything, R setup and some code is there. You can check it. You just install that R and just run that code. These are the lines in the blue form. These two folders will be there. In that distributor T matrix. You just have to open it and just copy it. Yeah, it's in that one also.
Can try also. Yeah, for that purpose only we can.
It's okay. This 7 PCs are installed. If anybody wants to try, you can try.
Everyone has a laptop.
I was able to end this laptop already.
You can show it from here.
Yeah, it's hanging the folder. So I wanted to extract. No, it's not responding.
The folder to extract.
Yes, this. Okay, now yes. But just, I don't know if I have extracted. How can I? Because I don't have the. Okay, extract. Okay, extract.
Or you can say extract.
No, it's here. It's not. Okay, user IITM. Thank you. So I will start executing from here just to show. Let me copy the folder. Okay, with this command, I'm just changing directory. So I'm just placing in the directory where I have the code. And with this source, I just load the main program. Was one more folder. Yes. Okay. Then I have to source the program. Okay. And then I can execute it. So before I give this command just to stop, the graphics from refreshing, so we can go one by one, because this is a processing 1 day of disdrometer measurements with T-matrix scattering simulation of the radar parameter. So we can see minute by minute the evolution of this event. So, and now to execute. Maybe I will directly copy from here. So this. Okay, it's Windows, it's different. Okay, so these are the drop size distribution recorded during 1 day. This is, precipitation started in the afternoon, so the first graphics that we see are at around 5 p.m. So these are the observations, and the numbers mark actually the number of drops in the corresponding diameter. So we had in this case 43 drops with diameter here. I don't know the number exact plus 7 drops here. So very few. And here we have some parameter of the distribution derived from fitting a gamma shape DSD to the observations. And if we move on, you see how the DSD was evolving. Then we can go to some more interesting stuff. So here it starts to become more interesting, more rain, more rainfall, more DSD. And if you see it in general, the thing is, as a new, the new parameter is positive. It's 4.3. Okay. You can see this, how the slope is getting lower, and C0 is increasing. D0 is inversely proportional to the slope, to lambda. And this was an event in, just a couple of weeks ago in Italy. So it was a relatively steady precipitation event, not a heavy convection event. Okay, so that's all. So, and in this object, DSD, we have some of the radar variables simulated as the C-band and X-band. So we can actually plot both. I may refer to the presentation here to have a quicker look, and then we can do some other analysis on the R.
Yes.
Sorry?
I don't think anybody is keeping up with you.
Well, I mean, if that's not installed, it's difficult, but I will show now some results, and then give time to the ones who have are installed. Then I have also.
Because all the people have their laptop on, but I don't know what they're doing. And so, is anybody trying to follow him or do anything? Because otherwise he's wasting his time.
No, I can show this case, and then we can maybe with some help we can try to run another event.
Because I saw suddenly the whole dynamic here changed. That's why I came to the back.
These are the three blue colors. You just need to type them.
Yes, if you have R installed, it's as simple as this.
Yeah, part means you need to put your part. Don't put part. Okay. So you need to put the part like we type like that kind of source and it will automatically show that.
Mm-hmm.
Otherwise, some of the
At least one or two people keep up with that. There is a person. If somebody needs, okay, just install. You click downloading not install the name. You see, I think you need to.
Yes.
Yeah, like suddenly saw that. Last couple of minutes.
Somebody needs help.
Just give some time. Let everybody download or at least who wants to. There may be some people who don't want to join the hub region. At least somebody who wants to do. We try to keep up. Yes, no.
Are you trying to keep up with them or you're reading email?
Try to do something. Well, where are you now?
You just downloaded out? Okay, so everybody is still
Yes. So
5 screens behind.
yes. Now I can talk slowly about them and giving a bit more.
So these people who are attempting, we should help them.
Yes. Meanwhile, I will give you.
Okay, raise your hand. How many of you have just downloaded out? Okay. Maybe I was mistaken. Let's go slow. Even if
Yeah.
it's okay.
So after you download, you just give this command to set the path where you have.
Are you doing the mic?
Yes, I do.
Okay.
Maybe.
You move up.
The problem is when I look at the screen.
Yeah.
So the first command is to if you all have Windows, it's you need to go to the path where you have downloaded the code, so that then you can just use a relative path, and it's easier. Then you have to source the main program, this command here, and then to execute in this command where we pass some parameters. The first is the file name. The second is the interval, which is 1 minute in this case, and to mask true or false. And I will show you right after what is this meaning. The interval can be larger than 1 minute. The different data we collect are every 1 minute, but we can aggregate and show the distribution aggregating to any multiple of 1 minute. The mask is this one. We've been talking about the terminal pole velocity this morning. So since the distrometer, in the distrometer, there may be not reliable data because there may be drops splashing from obstacles from the same distrometer and then falling into the area of sampling of the distrometer. It is very common to apply masking based on the velocity diameter relation to filter out any drops that are likely not related with the rain. So we take the atlas velocity diameter relation, and we apply this mask. We set some boundaries, and we reject all the observation that comes from outside this region, because the velocity is not consistent with the size according to the theoretical relations. Of course, this is assuming that we are being rain. Of course, in case of hail, we should not mask with this. Yes.
Just give some break time.
Yes.
Just stop. 10 minutes.
Actually, most of them would like me to go back a few steps. They are short and they want to know how to start a process.
I'm going to use my friend from ISA.
Excuse me.
What do you want to know?
Try to download it. It is the one file. One PPT I have added. You just open that PPT. Just again go through the link, and there is a PPT is there. Just copy it.
Okay.
That PPT is in there.
Yes, you can also copy directly. If you don't want to type.
What I'm saying is just let's stop and give them some time.
Yes.
Don't say anything. Because it's hard for them to do at the same time.
Yes. I can stop. This.
So yeah. We were one for the top. And then I saw it. Avoid the terrible competition. Yeah, because no. Yes, you are right. I'm sorry, but you yeah. Search for just get to that. Yeah. Okay. Yeah. Yeah, I want to see. Yeah, you have to compress this and then read it as well. And yes. Oh, there is another. That's the reason. We can add another data. Data.
Yeah, one more bit. Okay. Yes. Yes. We can change it. And time. Because each is waiting. Was that, yeah. You see? You see? So this takes data each minute, every minute. Then, according to the size, giving the medical distribution, and then you get the gamma distribution for this
Okay, if you want to see. Yes, so this is. Each time you so can you get a patient data? Yeah. Yeah. You get the name. Also, you're saying, you're saying that you're still
So, can you hear me? I think that many of you have succeeded studying, so we can discuss a bit more now the substance.
Can you raise hand? How many of you have moved forward? Wow.
Wow. So what we are doing now? So this program, some of you, I mean, you've been able to run it. So in this object, which we call DSD, there are a lot of parameters that have been stored. So, and I will just plot from the slides, and then we go back to the program. So we are applying this masking just to filter out anything that is not rain. And that's the meaning of this parameter here, do mask equal true. You can run it with do mask equal false, and you will have some more droplets probably in the distribution and slightly different results. And then from from your object, we can compare the reflectivity at C band and the reflectivity at X band. So in C band is black, X band is red. So we see that in general, these are very similar, but in some cases, there are some significant differences like this. And then we can track this difference to the drop size distribution. So this is minute 1356. So if we look at this distribution, and you actually can go and check also with your code, we see that the minute before is this distribution, and you see that the maximum drop that we had here is we had 2 drops with the diameter slightly below 2 millimeters. But the next minute here, we have a few drops, actually 2, 2, and 1, especially this one, more than 3 millimeters. So, and then the following minute, we don't have any drops like this. And if we look at the differential reflectivity, we can compare CDR at C band on the x-axis and CDR on the y-axis, and we see that they are very close until about 1 dB, but then the X band is reaching higher value compared to the C band. And the reason is this. We've been talking before this morning, this P scattering peak at X band was at the diameter size of between 3 and 4 millimeters, while at C band it was only for larger drops. So since in this type of rain we didn't have a very large drops, it was I mean a couple of weeks ago. I mean late winter precipitation, and we only had drops until 4 millimeters. So in that case, you see that CDR, this is for a single drop, and for a single drop is larger. And when there are drops larger than 2.53 millimeters, then you can see these differences. So this we can see in the code. So basically, once you have run it, this command gives you information on the object, and you can see a lot of variables here. These are all the variables that have been simulated, and we can, for example, plot the DSD with the dollars like this. You can access the values of the individual variables. And yes, this, for example, will give you the plot of the reflectivity during the whole day. So there was no precipitation until the late afternoon. So this is time, basically. Every value is 1 minute. There are 1,440 minutes in the day. And these are the values of the reflectivity, about a bit less than 40 dBc, the maximum. And then you can do the same for reflectivity at X band. For example, we can add it to the same plot as lines. Okay, and then you see exactly what I've shown in the slide. Okay, it's enough to zoom in to see a bit more the details. And for CDR, we can do this plot CDR at C band versus CDR at X band. And we can add the bisect to see. Okay, and you see this the effect of this scattering at X band, and this is actually often more visible in the differential reflectivity than in the reflectivity itself. I mean, the relative impact is typically larger. So I think that this is, I mean, if we look again at reflectivity, maybe I plot it over a a smaller range. Okay, so this is the horizontal reflectivity at the C band and X band. So I think that this is a chance we were talking about again to remark the difference between the reflectivity factor and the reflectivity which is that the radar observes. So the reflectivity factor is defined as the integral of the distribution times d to the 6. And this is like a property of the precipitation medium, just like a rainfall or the water content. So it is not related to scattering. The other thing is the reflectivity that we get from the radar. This is the result of scattering. So it changes depending on the wavelength that we use. So to compare the reflectivity from a disdrometer with the reflectivity that we observe with the radar, we need to do the scattering simulation and get the proper reflectivity for that specific frequency. Otherwise, if we simply calculate the reflectivity factor as the integral of d to the 6, we obtain a meaningful variable, but it's not related specifically to the radar. I don't know if this is clear. That there is often a confusion because we call reflectivity different things, but the reflectivity factor is a property of the medium. It's not related to scattering, while what we call equivalent reflectivity or observed reflectivity, since it has been observed with the radar, it is dependent on the radar and on the wavelength that we have used. So depending on the scope of the analysis, you may be interested in the reflectivity factor, then you can simply calculate without any T-matrix calculation. You can calculate with doing the integral of d to the 6, very simple. And that case, it is also useful for S-band, for example. You can rely on that because for S-band is very similar because S-band for rainfall is all Rayleigh scattering. So in that case, it is the same. But for higher frequency, for C-band, X-band, and higher, then you need to do the T-matrix calculation like we did with this code to make a comparison.
Yeah. For ZDR.
Yes.
So yeah, once your radar should be well calibrated, I understand. So in post-processing, what will be your
In the post-processing, yeah, like ZDR. So for a good ZDR, your radar should be well calibrated. We can do one scan and do those calibration, but still the ZDR will be noisy. So in the post-processing, what are the factors we should consider so that we can get a good and reliable ZDR, apart from that attenuation corrections and the thing?
Yes, we've been talking in the coffee break. Actually, you can first look also at the scan parameter of the radar, because if you are not satisfied with the quality of CDR, it may give you the fact that maybe you are integrating too few pulses. Maybe the antenna is scanning too fast.
So then again, another question will be like, what should be the optimal RPM like?
Well,
RPM, because if you ask company people, they will say that get 1 RPM, you will get a very clean data set. But it is like you will lose a lot of
yes. I mean, in the radar, it's always a compromise between different things. If you want a very high quality observation, but like 3 degrees per second, you collect more than 100 pulses, and you have very high. But there are curves that show the standard deviation of the observations with respect to the number of pulses that you integrate. So there is the curve goes like this. So there is a strong increase in the accuracy at the beginning, but then it tends to.
Chapter 7.
Okay, Roberto has this slide for tomorrow. So of course you can also look at this and decide what is a decent number of pulses that you may need to get the desired accuracy. Then, if you don't get that type of accuracy, then probably you have to look at if there is something wrong the radar. And the other thing, in the post-processing, you can do something like range averaging, try to increase the accuracy at the cost of reducing the spatial resolution.
Yeah, so how many beams you suggest? Like, maybe it means like,
yes.
Depend upon like resolution, but like suppose we can go up to like 1 kilometer or 2 kilometer range.
Well, it depends also on the precipitation type, because for convective precipitation, if the scale of physical variation of the precipitation is very small, you cannot average 1 kilometer, because of course you have to choose range averaging over a distance where you assume that precipitation is uniform. So, and also depending on the dimension of your range resolution. If you have 150 meter range resolution, maybe starting from precipitation, you can integrate 4 to 8 ranges, and you get a very good estimate of CDR. Maybe in convection is not that easy because you may have stronger gradients, physical gradients in CDR. So then averaging maybe you don't get that type of accuracy.
Yeah, in continuation with that, like you do attenuation corrections. So how about in the melting layer and the snow region? If you don't consider that thing that will overcorrected and then do, so what will be your solution?
We do like we only correct for attenuation until the freezing levels. So, and this is, we get it from model input, we get the height of the freezing level, and the attenuation correction is corrected only in the freezing level. That's a very good point, actually, because in ice, we did not talk about ice, but you can have a very high increase in differential phase shift due to ice crystals. So if you correct for attenuation, applying relation based on rain in ice, may actually overestimate a lot. Yes.
Thank you.
So maybe we can to finish. We have another event that I loaded in the same folder. That is just you can run the program with the different data. So this was March 21st, and I think what I have is okay. I have to change also the directory here. Okay, yes, it's 20 August 2 last summer, August 2 last summer. So we can look at this. This was a really convective event. So we have a much higher reflectivity and rainfall rate. So I will go, okay, a little bit, but you may have seen some very long tail distribution. I can show it maybe with in the slides. So why it's moving like this way? Okay. Okay. Yes, this is the case that I have just run. So there are cases with you see 3 drops in range between 5 and 6 millimeters. So actually for this precipitation type, we expect a big impact also on C-band, because this is the main region for C-band. And in fact, if we compare in this case the reflectivities, this is a reflectivities as the X-band reflectivity is still higher than the C-band. But if you look at CDR at C-band can reach value as high as 670 B. This was referred to this specific distribution. Just because of these few drops, then you get this very high value. So you see CDR around 2 dB, X-band is higher, but then above 2.5, then C-band is higher. And this is all because of the p-scattering ripple happening at different size parameters. So this is, I think, a useful exercise to understand also the specific dynamics of reflectivity and differential reflectivity. But as I said before, you often see most impact on CDR respect to reflectivity. Okay, so I think that this is what I have. If you have a question, any question on this analysis?
Yeah. Any questions?
Do you like art? You didn't know. Very useful.
That's important. It's been pushing art all night.
No.
Like art,
I don't have a percentage of it.
art. Like art.
Yes, there is also a Python package. It's called PyDSD that you can download and you can things. And actually, I think it's connected with Pythematics, so you can do can generate simulation for any frequencies. In this case, we have used a lookup table for C and X-band. But that Pythematics it's a bit older, so probably it's not compliant with the latest version of Python, but with the container with the older version. While R it was much easier for a quick install and execution.
So it will plan for the ideas. You said the person control and everything.
Hello.
Hello. Actually, in the previous PPT, there are first.
This?
Not the previous PPT. When you are showing the PPI of reflectivity and ZDR.
Ah, okay. Just. You mean in the melting layer? This?
Not first plot. PPI of third plot.
This?
Yes.
Okay.
In a near about radar, there is no reflectivity echo, but very high random.
Yeah.
Why that is occurring?
Okay. First, I think I just noticed there is an error. So this at 5.8 degree elevation, this is at 4.4. But this is not the main reason. So this is just clutter from side lobes. Our radar is on the hill near the city, and there is when you have a radar on the plane, you don't have that much side lobe contamination. But for a radar on the mountains or on the hill, you have the radar is here. This is the mountains, and you have the main lobe. But the side lobe, there are side lobes that will point to the ground and will give a lot of additional clutter, but with very weak intensity because it comes from side lobes. So it's actually below this threshold here. And but you can still see in CDR. Besides that, I think that probably this Z here is filtered with clutter, but probably this is CDR view. This is unfiltered. So actually, this is not a fair comparison. Probably in the unfiltered reflectivity, we also have some echoes here. Typically, it's weak because it's from side lobes, but we may have also something here. But actually, we are comparing. Yes, this is not filtered, this is filtered.
Actually, when this kind of the echo happens, it's random area because of the side lobes. Some correlation also match, and if we apply the SNR about the filter out all the echoes below the 10 dB, still that random ZDR values are happening. How to filter out those kind of there?
Well, if you have the Doppler filter implemented in the signal processor, also these clutter echoes from side lobes should mainly go away. But besides that, we have post-processing cluster identification that consider the variance, the textures of CDR, TDP, and the value of ρHV to discriminate whether it is meteorological or non-meteorological equals. And typically, we are able to, completely remove these non-meteorological equals.
In that sometimes, most of the time I have seen the ρHV also, we get the higher value of ρHV, about the 0.9 in the, whenever there is no reflectivity. In that case, there is a bias that those could be due to the bias in the ZDR bias.
Well, I don't know. We should actually see the data.
Yes, data. Yes, it's like you have something in mind.
Yes, it's
You have to
difficult.
keep asking the questions so that you see. We have the data, we can look at it tomorrow, or even this evening. Can you show the data to us?
Can you show the data?
Yes.
Mobile radar?
Yes, Bhopal, right?
Okay, let's see.
Yes, maybe we can discuss something tomorrow.
Okay. Yes, I have a question. Why there is a time gap between ZTR column and the maximum?
Okay. So the physical explanation that ZDR column is a marker via draft and carrying a lot of drops that become supercooled lost. Then this also can become embryos for a formation. And then, so there is the process of precipitation growth. So then comes hail. So it takes time to form, then hail will come down. So there is a delay between the ZDR column lost and the maximum precipitation at the ground. There is also a delay between the maximum reflectivity aloft and the precipitation at the ground, but this delay is smaller typically. The ZDR column is a precursor, even comes even earlier than the higher reflectivity aloft.
From morning slide, you showed a ZDR column, and the ZDR column, there is like a lot of intense values at the bottom where there are the heavy droplets accumulating, and at the top. But in between, through the column, there is a reduction of the intensity. So why would that be?
But you refer to this slide?
If you would open up
These slides here?
I don't see them here, but in the audience, the ZDR column you showed.
Okay, in the chill data probably. It was the supercell. This one?
So the curve on my right. So there is like ZDR is a lot of redness, the 20 to 15 range. That is understandable, and a lot of red colors over the top. So probably the drop carrying these heavy droplets. But why is it yellow? The droplets are going through that passage, right?
I don't know. I think one speculation could be that there is an equilibrium between the drops and the updraft. So probably medium to large drops are almost stable, and then of course may go for priming and so on. So depending on the balance between the updraft and the terminal pole velocity, I mean the smaller drops which have a smaller pole velocity will be carried further aloft, and the very large will fall. And probably there is an accumulation of drops due to the fact that there is an equilibrium between the vertical velocity and the specific size. But so this is, I've been speculating. I mean, but maybe there can be many other reasons. We should also look at three-dimensionally. This is only one slice.
I guess I'll read a bit about it. One more thing. So the ZDR you showed in these slides. So there is a lot of missing data in between the slides, right?
Because that was a cut to a volume scan. It was not an RHI.
Okay. So do we usually get that many missing data, or?
It is 10 sequence of time.
Yeah, so there are gaps in between. Yeah. So there are like I can see the individual scans, but there are like gaps between.
Yes,
Open up.
because it depends on the scan strategy. Because if you have, one PPI every 1 degree, you would not see this gap. But we have elevation starting from minus 0.1,
Yes.
0.5, 1.2, 2, 3, 4.4, 5.8. Then you see the gap because the spacing is larger than the beam resolution. Okay.
So the gap is that must be resolution.
Yes, and then you see this is 15 degrees, this is 28.
So with this scan strategy, I will always take steps.
Yes, yes. This is just the geometry of the scan. Because this is a cut after the volume scan, it's not the RHI scan.
So in the context of side lobes, whatever you are getting in the radar side, that side lobe is related to antenna, not to the NLFM. We have two types of side lobes, pulse side lobes and antenna side lobes. That is regarding antenna side lobes. What is the typical levels preferred to avoid this kind of problems?
One thing is, which you don't pay a fortune. So what, you should get minus 25 dB side lobe one way. So that should be a reasonably priced antenna. Then you pay a lot of money to the antenna, like the CSU chill. Then you can really push the side down. Then for that you can have to offset. This is I'm talking about centrifugal reflectors. Simplest test.
The questions?
Creating that pulses. In a single beam, how many we have to consider? How many pulses?
So, okay. The thing is, the rule of thumb is, as the radar scans, you don't move beyond one beam width. Okay. In the integration scan. So typically, I myself, a lot of operational people, they integrate 30 samples and 24 samples and keep going fast. I'm a researcher. I typically don't take less than 100 samples. Because he pointed out, I was just looking at chapter 7, and the curve first very rapidly in the beginning, then it starts settling down. So if you don't take enough samples, then scan too fast, CPR will be nice. But that matter, even reflectivity will be noisy. But people have accepted that level of noise. But one thing about dual polarization radars is this, again, very high level statement. A lot of people, before dual polarization came, got away with murder and daylight robbery operating radars. Radar will be off by 5 dB. Nobody will know. You look at the picture, at just 5 dB, it just looks like another storm. But once dual polarization came, you make any mistake, it will be in your face. You have to deal with it. So the even clutter will just merge with reflectivity. But if you put clutter in dual polarization, it will be in your face. That's one of the big advantages. So when I this is almost a joke, but it's pretty serious. Canadians en masse shifted to dual polarization. They don't, well, they get some hailstorms in the summer. So I asked the people why they shifted to dual polarization. They said it's for 3 reasons. The 3 reasons are data quality, and data quality. That's what they said. Because reflectivity radars, they have been just committing international fraud all these days. Radar will be off. There are places I know in one country in Europe, I won't mention the name of the country, the radar was off by 5 dB. And comparing with gauges, they have come up with the ZR relationship. After some time, they suddenly discovered the radar was off by 5 dB. And they told, because that radar is controlled by hydrology community, they said, don't fix the error of 5 dB. then all is our relations are going to change. So that type of problem. So dual polarization and nothing else. It's brought the data quality issue to the front. Because rho-HV will tell you immediately if anything is wrong. It's a very beautiful property of precipitation. Only rho-HV is very high. Oh, because you asked number of pulses. So I actually had a slide to address your issue. If you scan too fast, then don't integrate enough, and then the thing you'll see it pulling in the display. Or when if you scan too slow, it look beautiful, but the storm would have changed. So the right balance is there are some equations. I don't know if it's in my old new book. In the old book, scan rate and the angular velocity, then related to the number of samples you collect. There is a connecting formula. It's given. The basic rule is you don't move beyond a beam width. If you move beyond a beam width, then you will get into the disagreement we were discussing with Swarup yesterday. Did I answer your question? It's been bothering him since yesterday. And he tried to catch me in 2-3 coffee breaks. I kept telling him I'll tell you later. So he probably thinks I don't know the answer. Any other question? This has been good. And also, just a small change. You might have converted everything to R, and I think the MATLAB subscription he doesn't still like, but you don't use MATLAB, right? So you're okay. And, most of you used R for the first time, and you got working within 10 minutes, right? You know, this is India, it's IT country. Can we close? Close today?
It's time, Dr. Reflectivity, and we have a few more announcements before we close. Firstly, please submit your DADA forms by tomorrow positively. Next, the participants can have their dinner at the Prithvi hostel using the coupons which were provided on the first day. The visit is on 10th. Not tomorrow, the visit is on 10th of April, and the certificates for the workshop will be given there itself. 10th of April. Tomorrow we'll be having the same session here at 9:30.
Yeah, that is very important. In case tomorrow, how many people are participating? Okay. I think Elon has a question.